Hello again, folks, in 114. Today, as promised, I will be going over the solutions to MAT-114, the final exam. By now, you should have the PDF if you're watching this. Basically, it looks like this. It's quite hefty, I have to admit. It's like, I think it was 26 pages, something like that, all combined. But the last 3 pages are just resources, they're tables. So if you have that printed, that's great. And we'll go over these. All right. And that's it. All right. Now let me fire up. Oh wait, just to verify. It's a good tradition, right? Today is Monday, the 10th of May, and that's why we're covering the final. All right. The official semester for Middlesex ends on Tuesday evening, technically into Wednesday morning. So this is our last day. Okay. I'm a little concerned this may run a bit long, so I'll go through it a bit quicker than I would normally. Historically, these types of videos will be being like 3 hours. Okay, let me just put it here. And I don't know if I need to do it close. Put my glasses on. This. I'll try to do this overlap, like superimpose the solution next to the question. Okay. Here's the final exam. It covers chapters 4, 6, 7, 8, and 12 in that order. There's weirdly 62 or 63 problems, but that's just being thorough, I thought. Okay. All right. Now, a couple of things. This is, we're going to be converting from ancient Egyptian hieroglyphics to a standard Hindu-Arabic numeral. All right. In order to do that, works. As I said, in the very back of the packet, especially if you're doing these type, is a table where it translates the Hindu-Arabic, the ancient Egyptian hieroglyphic into the standard numerals. Okay, notice that they're all powers of 10. And basically you're just adding. If you wanted to express a larger quantity, you would draw more of the symbol, which it's not efficient really. Not to disrespect it, but anyhow, some things are more intuitive than others. All right. These symbols, which to me, I don't know what it is, but they remind me of Fire Flower from Mario Brothers. I believe it's a moon, and then there's something of an arrow pointing into a circle here. This is a lotus flower according to the description of it, but this represents 1,000. Right? So if you have 1,000 of these, you could literally write 1,000 plus 1,000 plus 1,000. Or being that we're a little bit more sophisticated since ancient Egyptian times, we could employ some multiplication here. Because remember, multiplying is adding efficiently. The symbol that is adjacent, which looks like a sort of intersection symbol in math speak, right, is a heel, all right? So this represents 10. And since there are 1, 2, 3, 4, 5, 6 of these, you could again just add 10 plus 10 plus 10 plus 10 plus 10 plus 10. Or simplify your life and say 6 times 10. The next, that green will cooperate today. These are staves, I believe they're referred to. They're intuitively like a finger. There's another symbol that is a pointing finger that's not the same. This is literally just one. And there are 1, 2, 3, 4, 5, 6, 7 of these. So you could add 1 plus 1 plus 1 plus 1 plus 1 plus 1. 1, 2, 3, 4, 5, 6, 7. Or just simply write 7 times 1. And then do the multiplication first, just because it's faster. Alright, and in which case you'll get 3,000, of course, plus 60 plus 7. Alright. So 3,067 is what you end up with. The way that I wrote the problem, you're not really responsible for doing it the other way. Alright. But if you're curious, alright, if you had to convert it vice versa, just pay, like let's just say you started with this number, 3,067, and you wanted to convert it to hieroglyphic symbols. Alright, remember that Egyptian is working with powers of 10. Alright, it's really just adding. Alright, if you're going to express a larger quantity or a smaller quantity, you would simply not write the extra symbols. Alright, what you should do is pay attention to the number of places in a situation like this. Count places. This is the thousands, right? This is the hundreds. This is the tens place. And this is the ones place. So since the ancient Egyptian has powers of 10 symbols, what you would do is go understand that you're going to have 7 of the ones. So you would literally draw 7 stabs, right? 4, 5, 6, 7. All right. 6 heels would be 10. 1, 2, 3, 4, 5, 6. Nothing for the hundreds because there just isn't anything there. All right, and then 3 lotus flowers for the thousands. All right, just bunch them together. Don't leave a gap. And that's that. Okay, you're really just responsible for this, but the way I wrote the problem. But if you're curious, that's how you would translate it backwards. Okay. Now the next question is traditional Chinese numerals. In the case, the information that is important is in traditional Chinese, we are told that we have pairs that are of values stacked. Usually. There are some exceptions, like if you had 0, say, for example. The top is a quantity that is 1 to 9, and what is immediately underneath it usually is something that you multiply by, some power of 10. And once again, this is going to be a dud. Alright, so again, you have in the back of this packet, there's a table limited to the traditional Chinese characters from 0, 1 to 9, yeah, and then some powers of 10. You have 10, you have 100, you have 1,000. So, if they are in fact in pairs, then the way that you would read this that there are two things that you have to express a quantity in here and two here. All right. If you were more familiar with it, you go, oh, obviously that this is an even amount of them, and so there's exactly 2 and 2, and there's no 0 involved. So you would just kind of go to it immediately. Again, the figure on top would be something that is 1 to 9. All right. It just so happens that this particular character is a 6, and this character is 100. So that is naturally 600. All right. Down here, more intuitively, all right, is 2, and this is, I believe, 10. Yes. Okay. So this is 20. All right. And if you add them, naturally, you get 620. Again, you're not responsible to do it the other way, the way I wrote the question. But if you're curious as to convert it backwards, what you would want to do is try to break into pairs. Stacked, of course. With the same idea that the top is going to be a number that is 1 to 9, and just underneath it is going to be something that is some power of 10. If you had 0 in the middle, you would use this symbol. I'm not going to do it any justice unless I try to replicate what I did before, forgive me. This is actually my favorite. Because it kind of looks like a face. Better to do this with an actual brush, I would figure. And have 0 or in the middle, you would just use the symbol. You don't have to say 0 times something. That equals 0. So if you have the figure, let's see if this works, 620, I would analyze it again. You have something in the hundreds place, right? You have something in the tens place, and you have something in, well, technically nothing in the ones place. Right? So we'll try to break it into, since there is a 0 here, we're not going to bother putting anything at all. Right? It's unnecessary. Right? So if you have 0 in the middle, just use that symbol. If 0 on the end, right, exclude it. What we'll do is we'll try to break this into add-ends that are the places, but stacked. So you have 600 to start with, you have 20 to start with, and you have 0 to start with. Okay. This can be broken into a pair in this basic strategy. All right, the top figure being 1 to 9, that is the non-zero digit, and then what you would multiply by to qualify as 600. So 6 times 100, and then again a non-zero 2 times 10, and then this is unnecessary. Okay, so if again, just as a Westerner who is not familiar with traditional Chinese too often, outside of this glass, use a diagram like in the back here. What does 6 look like? It looks like this character, which, although I don't mean any disrespect to me, looks very much like a star. So I will muddle through. Not to make too many excuses, I still feel that this would be better if I were not writing with marker. But it is worth taking a chance to do it. Okay, so. I swear that's a 6. Times 100 would be something like that. 2 is intuitive. It's like Roman numerals, but sideways by comparison. And 10 is something like a cross. Do forgive me. It would be something like that. The instrument of, the implement for drawing would really help if it was natural to the system. So since this is ancient, I don't know if it's ancient per se, but this is historic, all right? You probably would be using a brush if you were actually doing this. It would come out nicer. All right. For Ionic Greek, what is down here? There are a lot of characters for Ionic Greek. I'll put this right. Is that visible? It's okay. For Ionic Greek, alright, just remember one thing. The character set, if you look at the back again, that you have to work with, and in theory, if you were a scholar from back in the days, that you would memorize, right, has figures 1 to 9, and then things like, the tens, so 10, 20, 30, 40, 50, 60, up to 100, and then the hundreds. Right, but it stops at 900. So there is no 1,000. Right? The way the book has decided to address that is to employ a superscript. Right? So if you see an iota symbol, which looks like, a lot of times it looks like a J backwards. It's really something like an I. What are you doing here? Go to sleep. This is an iota superscript. Meaning slightly higher, slightly smaller fonts than the others. Here are iotas. All right, it means times 1,000. Right. So, all right, you have something times kappa. You have something times delta, and then you have the regular characters tau, kappa again, and beta, right, and what they represent. Right. It just so happens. For this one, it's something times 1,000, and then it's something times it's 1,000 again, yes. And then it's whatever tau is, whatever kappa is, whatever beta is. All right. What is kappa? Kappa is 20 by itself. So 20 times 1,000, delta is 4. Let's see. Tau is 300. Kappa is already established as being 20, and beta is 2. And we're going to add all of these. All right. 2 times 1,000 is 2,000 with an extra 0 is 20,000 actually. 4 times 1,000 is 4,000. Plus 300, plus 20, plus 2. Right. In sequence, it's understood that you combine these. So we get 24,220. 22. Okay. Were you to go the other way again, just remind yourself you have symbols up to 900. Anything beyond that, you would have to use an iota superscript to imply times 1,000. All right. I would try it again, break into places. So, let's see if black works. All right, if this is your figure, 24,322, you would have, to start with, 20,000, 4,000, 300, 20, and 2, all right? You will have a symbol because we have symbols up to 900, so you could replace this, this, and this immediately. These things that exceed 900, you would, that is by another 100, would be times 1,000. So you would try to incorporate something times 1,000 with an iota superscript. All right. If you do these from maybe from the right would be a little bit more intuitive. The second letter in the Greek alphabet is beta, so we use a B. 20 is represented by kappa, which again I'm not really doing it any justice. It looks something like a K. All right. 300 is tau, something like that. Delta is 4. All right. Since this has to be something times 1,000, all right. If the digit is 4, then you would use delta and then an iota superscript. This is something times 1,000 again. So you're going to have an iota superscript, but you'd have to use 20 instead. All right, so we have established kappa as 20. So iota kappa, iota delta, tau, kappa, and beta again. All right, a little bit closer than I've written it. Go to the next ones, Babylonian and Mayan. Couple of things to remember. Just put it here for reference. This is ancient Babylonian. So Babylonian is base 60, right? Otherwise known as sexagesimal. Pronouncing that correctly. Sexagesimal. Tomato. Alright. So if it's base 60, right, the place value is not powers of 10, right? The places are powers of 60 instead. So you might start with writing that, right? And understand that since you have two groups here, there's an obvious gap. Gaps separate places. You're going to use 2 powers of 60 ultimately. So this is going to be something times 60 to the first, and this is going to be something ultimately that is times 60 to the 0. You really start from the far right to the left. It's a little, counterintuitive that way. And there's only 2 characters as well. There is the wedge shape, and then there's more or less the boomerang shape, right? The wedge shape is 10, the boomerang, is 1, and the wedge shape is, the boomerang shape is 10. You can subtract. If you see this symbol in tandem with a wedge under it, sort of a flukerang here, like that, that means basically something minus something. Okay, so whatever is on the left side of it subtracted by whatever is on the right side of it. All right. So we're going to convert this to a regular number. Okay. If this is just a single solitary wedge, then this is 1 times 60 to the 0. All right. If this is something that has those 2 symbols in sequence, the forward pointing arrow, I like to call it, a flukerang is a style, something from art, and it kind of looks like that, but over a railroad spike, right? But this means minus, right? So if you have a boomerang, that's 10 minus 2 fangs here is 2. That's the figure that's going to go here. All right. So 10 minus 2 would be 8. Right. Remember that when you have something base to a 0 exponent, that's going to be 1. Right. So this is really 8 times 1. Right. 1 times 60 is 60, and 8 times 1 is really 8, so if you would add them, naturally you would get 68. If you were to go the other way, again, you're not required to do that the way I wrote the problem. What you would do is write out the powers of 60. Right, as many as there are groups. Right, so in this case, in this case, places. Now I'm jumping the gun here, sorry. Write out the powers of 60 and then establish what they're worth. So, as mentioned before, 60 to the 0 is 1, 60 to the first is 60, 60 to the second is 216, I believe. No, let's see. 60 to the second. 3,600, what am I saying? Okay. So, and then you use this to compare. Put that down. Okay. You're going to compare to the places in the given. So, if your figure is 68, look at the numbers that you have up here. 68 is way less than 3600, right? And since it happens to be less than that, you're not going to use that particular power of 60, right? As soon as you see a switch from it being less to either equal or greater, right, as you would now, that's what you're going to divide by. Use 60 to divide into 68. How many 60s roughly can you fit into 68? Let's see. One whole 60 would fit in there, and then do the actual long division, you'd have an 8 left over. You're going to use this, right? So circle the quotient, right? And then you're going to keep dividing until you run out of places here, run out of powers of 60. So the next one is, you're going to divide 8 by the next power of 60, which is 60 to the 0, which is really the number 1. One goes in 8 exactly how many times? 8. Right, so we need to express these two quantities, right, which means that it's going to be 1 times something, technically 60 to the 0 first, and this is going to be a gap, and then this is going to be 8 times 60 to the 0 technically. All right, but we have to translate it into the Babylonian symbols, so thankfully there's only 2. I need a little bit of space, so forgive me, I'm going to erase a little bit. Okay, so we have, I'm trying to, should be standing in front of it because it's right there. The Babylonian symbol for 1, right, a gap, and then the Babylonian symbols for the quantity 8. Now since that we are limited to the characters 1 and 10, what that means is that in theory when we get here, we'd either have to add or we would have to subtract, right? I don't think it would be wrong if you added instead, in which case you would put a lot of the railroad spike, right? The Babylonian symbol for 160, right, is just the fang here. Then there's the gap to separate out the places. And then in theory, if we're going to go the adding route, right, you would make 8 of these. But notice something about that. 1, 2, 3, 4, 5, 6, 7, 8. That's not very efficient, right? So rather than do that, and again, I don't think it's wrong to do that, what you would do is, just for the sake of having to write less, is you would subtract instead, right, to express the same quantity. So going the subtraction route, we're going to subtract, so we're going to use that symbol in tandem with that symbol. This is minus, and then the quantity here is the 10 minus just 2 fangs here. Right. It's a little more efficient than having to write out 8 of these. Okay, something like that. Okay. Last of these, and then I will speed it up. After this point, after Mayan, we're not really using unfamiliar character set. We're just doing different bases. Okay. I really like these actually, the Mayan symbols, because they're very intuitive, right? A dot is 1, all right? A line is 5, all right? And this sort of profile that looks like a coin to me, or a football, all right, is 0, right? So it's round, right? Just like the symbol that we have for 0. It's not a base 10 system though. Right? Mayan, just to remind you, is sort of base 20. Right? It's not exactly base 20 because they incorporate 18 at one point in the places. So I'll put it up here. You have 20 to the 0, well and good, which is still 1. And then the next place value would be 20 to the first, well and good. And then it's 20 to the first again, but it's 20 to the first times 18. Right? The reason for this, I surmise, is that 18 times 20 is 360, which is very remarkably close to the number of calendar days. Right? This is known as, if it were a true base 20 system, vigesimal, I believe. A vigesimal. Read my pronunciation. The next place after this one would be still 18. They don't do 18 to different exponents. It would be 18 squared at that point. Right, so it's the powers of 20 that increase, but you would keep implementing times 18 once you get past this one. These are also stacked. The bottom is essentially the ones place. Is 20 to the 0. So if you were to take this and sort of chop it up now, you would see you have 4 groupings, like that. 1, 2, 3, 4. Right. This would be something essentially times 20 to the 0. This would be something times 20 to the first. This would be something times 18 times 20 to the first. And this would be something times 18 times 20 to the second. Right. The values of these, it might be worth the trouble to express them as the standard value that we have. Just so when you're dividing, it won't be a hassle. The 20 to the first is 1 naturally, this is 20, this is 360 like I mentioned. And this is 7,200. Sometimes you have to go another one just to when you're doing comparisons, but I'll skip that for a moment. All right. Now, as you're reading these again, they're very intuitive. You can almost get away with not having a table for comparison's sake. All right. A line is 5, a dot is 1. So if you see these in tandem, you see 3 lines, that's 5, 5, and 5 is 15, and then 3 dots. All right, so that would be 15 plus 3 is 18 times 20. All right, this is 1 line and 3 dots, which means that it's 5 plus 3, which is 8. This is a circle essentially, so it's 0. And this is 2 lines, 10, this is 5 and 5, and then 1 dot is 11. Okay, now this is really 18 times 1 is 20 to the 0 is 1, so you have 18, first level. Then you have 8 times 20, which is 160. And then this would be 360 times 0, which is just 0. And then you have this value, 7,200 times 11, which is going to be enormous. And let's see. $7,200 times 11, which is 79,200. Right. Add them all together. That's a 6, I swear. Plus 18. And you get this. 79,378. Which is the actual answer to this question. Alright, now again, you're not required to do this, but if you had to do it the way I wrote the problem, but if you had to do it the other way, convert from the standard Hindu Arabic numerals to these symbols, alright, remember that you're going to stack these, alright, and it goes from bottom up really, so the bottom would be the first value of 20 to the 0, which is really just 1. Alright. It would help, I'll add one extra one here. You'd have to compare to what the actual values are. So if this is 20 to the 3rd times 18, this next value here, which you're not going to end up using, you're just kind of having it as a frame of reference, is 144,000, I believe, but let me just verify. 20 to the 3rd is 8,000 times 18. Yeah. So this would be 144,000. Right. The value that you are given I'm going to, as before, compare to Mayan place values. Okay. So here's our figure, 79,378. This is smaller than this value of 144,000, which means we're not going to use this when we divide. Right? As soon as it switches to the point of it being exactly equal to or greater than the value, then you're going to divide. This is greater than 72,000, so we could appropriately divide this. Pardon me, 7,200, 7,200. So, if you take this value, 7,200, it's a little tedious, and divide it into 79,378, that's where I'll get out of the way. How many 7,200s can you roughly fit into 7,937? First 4 digits here. 1, right? And you would have to go about the tedium of subtracting. 7, 3, 7, that would be 0, bring down an 8. How many 7,200s can you fit into 7,300? Again, it's 1, which is 7,200. And the difference in this case is 8, 7, 1. And you're not doing decimals, and you're not doing fractions really. So you're going to keep this remainder and divide it again. 1, 7, 8. Keep this, because we can express this into Mayan characters, this quotient. All right. But we have used 7,200, so now we're going to use the next place value, which is 360. Right. How many 360s can you fit into a number that's smaller than 360? You might go, something wrong here. No. Remember, this is really 0. All right. You can't fit a larger quantity into a smaller quantity. Alright? So you're going to put 0 and save it. And then, because you've accounted for this place value, you're going to move to the next one. So you have 178 divided by 20. Alright, and now do it again. Alright, how many 20s can you fit into 178? Roughly 8 would be 160. And then you have 1 left over, so you're going to save that. And then you're going to keep going. You've done that one, you have 1 more. All right, when you get to 0, pardon me, 1. Stop going to sleep. Come on, wake up. 1 1 goes into 18 exactly how many times? 18 times. It is these quotients that I've circled that you're going to translate into the characters, all right? We could only do that once we have divided by these place values. All right? So for the sake of space, I'm just going to erase this. All right, remember, we're going to stack these. I'll try to stay in here because I'm obscuring the solution. We have the quantity 11, 0, 8, and 18. Right. You don't really have to put, that this is times 20 to the 0 times 20 to the first, 20 to the first times 18, and so forth. You could just translate these pretty much immediately when you're going this way. All right. 18 is intuitively lines and dots. So 1, 2, 3 for 15, and then 3 dots. Right. And then 8 is 1 line for 5, and then 3 dots. And then 0 is just 0, which kind of looks like a coin. And then 11 is 2 lines, 5, 10, and 1 dot. Like you have. Okay. This idea of basically dividing to translate, you'll see again when we get down here. All right. It'll go a bit quicker though because we're not translating it into an alien sort of alphabet. Okay. So the first one here is translate the Hindu-Arabic numeral. Everything that is our standard system, it can be written alternatively with a subscript of 10. That's just a label. All right. If you see subscripts, all right, it's just a label signifying the base system. Alright, so our standard system with a little 10 here is just an alternative way of writing it. What we're going to do is translate it into something that is octal. So we'll have some figure with a little subscript of 8 eventually. Alright, in a case like this, when we're going from what is basically familiar to something that is alien. All right, let's establish a couple of things. What is the character set? If it's an octal system, all right, if you remember MAT-114, all right, the subject of modular systems, all right, came up, in which case they always start from 0, those systems, right? An octal system implies that there are 8 characters, but you start from 0. So what you would see is 0, 1, 2, 3, 4, 5, 6, 7. 8 total. Right? Right. And this would be in powers of 8. So 8 to the 0, 8 to the first, 8 to the second. Maybe I'll put it over here. A to the third, A to the fourth. It's probably overkill to do that many. But to establish what these values are. To the 0 is 1. To the 1 is 8. This is 64. And then 243, I believe. No, pardon me, it's 512. That's 243. I keep thinking that. And this is 4096. Is the actual value of those places. Yeah. Okay. Now, we're going to take the value here, 5,478, and compare it to these things. If I went a little step further, it might make it a little bit more comfortable, so I'll do that. Where's my calculator? There it is. Just out of morbid curiosity here, what is 8 to the 5th? 32,000, yeah. All right, 32,768. It's those place values that you need to compare to when you're trying to decide what to divide by, essentially. So, 5,478 is less than this figure, the value of 32,768, otherwise known as 8 to the 5th. So we are not going to use that. It immediately, that situation switches that it's greater than this value, 4,000. So we're going to divide by this first. So we have this figure, and we're going to divide by 4,096. It's tedious, but we will do it. All right. 4 goes into 5,000 roughly one time, 4,096. We need to use the long division because we have to establish what the remainder would actually be. A calculator, unfortunately, is not going to tell you that. 8 minus 6 is 2. 17 to borrow is 8. And then that's 3 minus 0 is 3. And this is 1,382. Circle the quotient because you're going to keep that. All right. And then you're going to divide here. 1,382. Trying to be consistent here in the coloring. Divided by the next place. All right, we've used this one, so we're going to do the next one, 512. 1,382 divided by 512. One would estimate that maybe 512 you can fit in twice. Because if it was 500 and you did 3, it would be 1,500. It's too much. So I'm going to go put a 2 here. Alright, and then I'll do some scratch work here. Times 2 is 4, 2, 100, 1024. Okay, that's probably as close as you're going to get without overshooting it. Subtract as you normally would. If this is 12 instead, that would be 8. 7 minus 2 is 5, and that's 3 again. So you have 358. Circle the quotient, you're going to use that later. Alright. And then we keep going until we've exhausted all the values here. Right. Did that one. So we have this 358 divided by the next value of 64. 64 goes into 358. Take a guess, let's see. That's about 60, and that with 36 times 6 would probably be overshooting it, but let's just see. 64 times 6, 24, carry the 2. 36 plus 2 is 38. Too much, so it'd have to be 5 then. Alright, 64 times 5, 20, carry the 2, 32, that's close. Alright, so you're going to put a 5 here, definitely going to keep that. That's a 5, I swear. And then subtract. 8, 3, 38. Moving along here. We have used that. Next is this remainder in here, 38. And the next value that we have to divide is 8. 8 goes into 38 roughly 4 times, which is 32. And the difference is 6. And just because I'm running out of space, I'm going to erase that. We have used this, and we have one more. So we're going to divide 6 by the last value of 1. And that is naturally going to terminate very well. 1 goes into 6 exactly 6 times. Terminates. Okay. So So these figures that we have, 1, 2, 5, 4, and 6. One, 2, 5, 4, and 6 are what 5,478 in base 10 would look like in base 8. 12,546. Right. I'm using a comma just more or less out of my conditioning, but we're not really in the base 10 system anymore, so I don't know if that's really good etiquette or not. Anyhow, 1, 2, 5, 4, 6, base 8. Okay. That's going from a familiar system to an alien system. Now, if you do 7, you're doing exactly the opposite of that. You're going into from a base 16 system, hexadecimal, into the familiar system. So from alien to familiar, my fam. Okay. The base 16 system, otherwise known as hexadecimal, that's what computers use at some point, looks like this. The character set is 16 total characters, and you start from 0. So what you're going to see is up to 9 that looks normal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then because we need a single digit wide character to express quantities greater than 9, right, we use the alphabet. So instead of calling something 10, 11, 12, 13, 14, and 15, because we stop at 15, remember, because we've already included 0 to make it 16 total. It's A, B, C, D, E, and F. All right. A is 10, B is 11, C is 12, D is 13, and so forth. Okay. If we're talking about a base 16 system, that means again that each of the places, instead of being powers of 10, the powers are 16. So we have, let me put it here because it might make it a little bit easier to read it. 16 to the 0, 16 to the first, 16 to the second, 16 to the third, 16 to the fourth. It might be overkill to go that far, but whatever works. All right. Note the number of places. Given. So in this funny number here, EAE1 is 1, 2, 3, 4. So of these powers of 16, we need that one, that one, that one, and that one, not this one. Right? Because we only have 4 characters. Okay? So if this is, the first digit here is E, it would be E to the 16 to the third. And this one would be A times 16 to the second. And this would be E again, times 16 to the first. And this would be just regular ordinary 1 times 16 to the 0. We can translate these into what they would be in the standard system, because again, we're going to a familiar Hindu-Arabic numeral system here. E is really representative of what character? That's 10, 11, 12, 13, 14. All right, so this is 14 times 16 to the third, which will be huge, right? And this is A times that would be 10. 10 times 16 squared. And then this is just 14 again, but it's times 16. And then this is just 1 times 1. 16 to the third is huge, right? What you end up with is this ultimately. 16 to the third is 4,096. This is 14 times 4,096. 16 times 16 is 256, I think. Yeah. This is 256, that's just 16, that's just 1. Alright, so 14 times 16 to the third is 57,344. Times 10 is 2560 plus 14 times 16. 224 plus 1. You should get, when all is said and done, 60,129 in base 10. Yeah. Okay. In my opinion, that's the hardest. That the stuff that we were talking about translating is the most challenging material from this semester. Maybe because for the lack of familiarity, because it requires a lot of things that you can't even get away using your calculator. You have to go through the tedium of it. Anyhow, it's interesting mental exercise. Next, some operations. Let me get some water. There's 3. There's adding, subtracting, and multiplying. When you add, you have to remember to add in the base system. And when you subtract, you have to remember you're borrowing in the base system. So just a couple of reminders here. When you add, remember you're going to carry. In the base system. Yeah. Okay. Later on, when you subtract, you're going to borrow in the base system. In between there and there, pretend as you go about your process, pretend that you're just adding as you would normally. Okay. What I would again encourage you, not to make a speech, is that when you were teaching, you're not going to teach this to little kids, obviously, but when you were teaching kids how to add regular numbers or decimals, give them graph paper so that they can collimate. Right? They'll be less likely to make a mistake for the reason of having sloppy handwriting, because they'll have some guides. Right? So like the bump is on at a bowling alley. You know, we won't make mistakes because of handwriting, right? Anyhow, we're going to just add these as we normally would. Right. This is the first column of add-ins, right? So I know it's base 7 in this case, but what we're going to do is we're just going to add as if this was regular 6 plus 2. All right. in which case we would get 8, right, in base 10, if this were the case. Right. What we do need, as a side note, is to express the characters of base 7. So I'll put these here. The characters of base 7 would be 0 to 6. So as we're doing our arithmetic, right, we're not going to see in the answer anything other than these symbols. Right? There's 7 total because it's base 7, but he's starting at 0. Right? Base 7 would have these place values: 7 to the 0, 7 to the first, 7 to the second, 7 to the third. This is really 1, 7, 49, and then with 7 cubed. Offhand, I don't even know if you need that. 343. 343. A frame of reference at the very minimum. Right. We're going to translate this into something in base 7. I want to see if a trick works. I mean, I would be a little leery of it anyway, but if you have the character set and it's finite, it's not too many things, and it goes up to 6 here, one extra one would be 0 here, right? And then another extra one would be here. So perhaps this is actually equal to 1 here. The way that you can verify that is doing the actual division, which I'm inclined to do. So the value here, 8 is less than 343. So we're not going to use that value. All right. 8 is less than 49. Right. So we're not going to use that one. All right. But 8 is greater than 7, so we're going to start here. All right. That means you're going to divide 7 into 8. Right. How many 7s can you squeeze into 8? Obviously, just 1. 7. Difference is 1. Okay. We have to go the whole 9 yards, so we're going to go one more here. So we'll divide 1 by 1. And then what do you get? 1 goes into 1 exactly 1 times, which is 1, and then terminates at that point. These are the values. 8 in base 10 is actually 11 in base 7. So my assumption that I could just count ahead is incorrect. All right. It's good to look for shortcuts, but better to do the arithmetic to verify. Confirm or deny your suspicions. All right. So 11 base 7. All right. Now, what again does that mean? It means that when you're doing the actual work here, we're going to carry in the base system. Since this is something base 7 plus something base 7, our solution has to be in base 7. So I'm going to put 11 by sticking a 1 here, and then I'm going to carry an extra 1 up here. Right? And now the focus is on this column, right? And it's just adding, thankfully. So in this case, what do you have? You have 1 plus 2 plus 6. Pretend it's just adding normally. So it's 1 plus 2 plus 6, right, which would be 9 in base 10. Perhaps it's now, since we have something established here, that 8 to the base 10, 8 base 10 is really 11, right? Perhaps this is 12 in base 7. But I would go through the arithmetic to confirm or deny that. All right. If you went through this process now, very similar to before, all right, 9 is less than 343, so again, you're not going to use that place value to divide. All right. 9 is less than 49, so you're not going to use that. and then, but 9 is greater than 7, so you would indeed divide by 7. Okay. So 7 goes into 9. How many times? All right, still once, which is 7, and the difference is 2. I'm going to keep that and divide again. 2 divided by 1. The next place value is 1, which is exactly 2, and it terminates. And the assumption is correct. Right? This is in fact 12 in base 7. So you're going to put a 2 here, and then again carry in the base system. All right? And again, you're going to pretend, you're going to just ordinarily adding, right? So now it is 1 plus 6 plus 5. 6 plus 5, which would be 12 in base 10. Again, you could kind of make a guess at this point. I'm still anal retentive, and I would still be careful. Right? But if it is 8 is 11 and then 9 is 12, that's 3 apart here, and that's 3 apart here. This is probably 15 in base 7, but I would still go through the process to verify. Let's see, we have 12 is less than 343, not going to use that. 12 is less than 49, no. The 12 is greater than 7, so we would logically divide by that. How many 7s can you fit in 12? 1. Which is 7, and the difference is 5. Which you divide by 1 is going to be 5 again, yep. So it is indeed 15. Okay. And since you're running out of places, you're just going to write that 15. All right. The sum of 626 in base 7 plus 562 in base 7 is apparently 1,521 in base 7. Okay. Uh-oh. I hate when it does that. Alright, let's do this. This one I stole from my lab because to me it was the most challenging of all of them, at least to me personally. All right. Again, be a good teacher, give your kids some graph paper. All right, might seem a little cuckoo, all right, but neatness helps, all right, in math world. Now, the basic strategy is we're going to borrow in the base system. All right? In this case, we have binary systems, so we're going to have base 2, which is also known as binary, has 2 characters, 0 and 1. All right. Something that might make you a little bit more comfortable is this basic truth. All right. 0 in base 2 is equal to 0 in base 10. All right, and vice versa. All right. Similarly, 1 in base 10 is also 1 in base 2. Knowing that will get you pretty far. All right. We're still going to subtract. Subtracting as normally to start with. All right, so this first column here is going to naturally be 1 minus 1, and regular ordinary 1 minus 1 would be 0 in base 10. What would it be in base 2? All right, well, just with this basic assumption, which is correct, you could go ahead and just, go, all right, it's definitely that. It's 0. Right? This is going to be 0 in base 2. What's the proof of that? Well, you could establish what the places are. If you want to verify by dividing, right? 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the 0 would be 1. 2 to the first would be 2. 2 to the third, I want to skip that, squared is 4. 2 to the third is 8. If you were to take this figure and compare it to these, it's less than 8, so you wouldn't use that. It's less than 4, so you're not going to use that. It's less than 2, so I'm not going to use that. And it is less than 1. Alright, so you might say, well, I'm not going to use that. But it just so happens that you're at the end here, right? And you know that if you divide 0 by 1, what are you going to get? At this point, you have no choice. One into 0 is 0. Right. So this is true. Okay. If you want to verify it, it's probably just easier when you're doing binary to memorize these two facts. It'll get you pretty far. Okay. Now, what happens here is you end up having to borrow, right? Look what you end up having to borrow a lot. You're not just going to borrow from the column that is adjacent. You end up having to go all the way to the end, right? So you would want to borrow from what is immediately next to it, but you can't because it's 0 there. So what you end up having to do is to borrow all the way from the far left, in this case. All right. Now, you borrow in the base system, which means that you're going to cancel this, right? And you're going to put 0 in this column. Right, because you're borrowing from that, and the most you can take is just 1. Right? What are you giving to it, though? What is going back this way is 2. Right? And that would be fine if you were just going for the adjacent column. But what you end up having to do is going back here to there. Right? And in the process, that is along the way, this 2 is going to shrink to just 1. Right? So this is tedious, right, and a little bit screwy, all right, but this is correct, all right? You borrowed in that base system number, ultimately, all right? When you're reducing, I know you might go to yourself, well, why didn't I put a 2 here? All right, because you can only change it to the character set that you have, right? Either 0 or 1. So what's 1 less than 1 naturally? 0, right? When you're giving to the adjacent column, though, you borrow, you're giving in that base number 2. And in this instance, it's only temporary because you have to go all the way back to the, almost the far right. That's why this 2 that was temporarily here gets crossed out and becomes 1 ultimately. Right? Now again, you pretend that you're subtracting as you would normally. 2 minus 1 is equal to 1 in base 10. We were doing regular base 10 system here. All right, what would that be in base 2? All right. 1 in base 10 is 1 in base 2. All right. You could check it with subtraction. I'm going to just for the moment fill in what the answer is here. All right, it's 1. And if you want proof, all right, here again is the process, all right, as you go through it. All right, the figure is 1. You compare it to what would be 8. This figure is too large, so you're not going to use that. All right. 1 is less than 4, still not going to use that. 1 is less than 2, you're still not going to use that. When you get to this one here, this is exactly equal to it in this case. The only exception that you could really have no choice is 0. But 0 is special. Alright. Anyhow, if you divide 1 by itself, what do you get? 1. Right. 0 is 0, 1 is 1. That's the best advice I can give you in terms of binary. Okay? That will make what's following a lot easier on you. Alright? The leftover 1 in this third column, minus the 1 that is there, is just what? It's 0. Alright? And since 0 is already established as being 0, we don't have to worry about it now. This is 0 and then there's nothing underneath it. So if we're going to maintain 4 distinct places, it would be 0, 0, 1, 0. Alright? And that is the answer. Yeah. Here's 10. Alright, now since this is multiplication, we're going to have to add at some point naturally. A thought just occurred to me. In recent history in the United States, the way that I'm going to multiply has been kind of poo-pooed, and it's unfortunate because there's really no other way to teach this. So, the old-fashioned way, you really need to know how to do it. Alright, here again, graph paper, alright? Give your kids graph paper, alright, when you're teaching them especially how to multiply, alright? Even if it seems a little crazy, right? Because the neatness will help you maintain the, will prevent you from making a mistake. Right, so there's a line here, and eventually there'll be a line here. The reason that I know it's going to be a line here is because you're multiplying by a 2-digit number here. Base 12, if you're curious, is known as duodecimal, like the dynamic duo. And consider what its character set would look like. It's always going to be 0 up to 9, but then beyond that you'll use letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. 0 to 9 is 10 characters. We need 2 more. To represent 10, we're going to use A. To represent 11, we're going to use B. All right, now there's 12 total. Sorry. Let's establish what the place values of base 12 would actually be. All right. 12 to the third, 12 squared, 12 to the first, 12 to the 0. I think you can get away with just using that many. Let's see. Yeah, it looks like it's alright. Alright. What are these worth? 12 cubed is 1728. 144, 12, and 1. It's the actual place values. Okay. Now, as before, we're going to pretend that you're just multiplying like usual. Okay, and then you're going to translate to the system as you're going through it. Right. Right, to base 12. Okay, here's what I mean by the traditional way to multiply something by hand. The way that you would do this is that you would stack them so that the longer number, it isn't necessarily greater, but whatever is longer is on top, and whatever is shorter is underneath it, like so. Okay, and then you do this times this, and you more or less distribute that first digit to each of the top digits. Then you make a place here, and then you do this digit times this one, this one, and this one. Again, you distribute the bottom digit, in this case the second one, to each of the top. Right? And you have them aligned like so. This, unfortunately, has been regarded as too old-fashioned in recent history, and that is unfortunate because now when you're doing something more complicated, you have no frame of reference. So we're going to make sure that you are clear on this. There's a lot of stupid ideas in education that have to be fixed. All right, that's one of them. Just throwing away something because it's old. All right, don't do that. I mean, I'm making a speech again. 4 times 3 would be, just coincidentally, the number 12, all right? In traditional base 10, if you want to be more comfortable. But we have to convert that to whatever it will be in base 12. Okay. So, you're going to compare this figure to what is in red here, right? 12 is less than 1728, we're not going to use that, right? 12 is less than 144, we're not going to use that. 12 is exactly equal to this, so we will divide 12 by 12. In which case we'll get 1. But remember, don't just stop there, go to the next one. And then you can divide 0 by the next value, which is 1 here, and you get 0. So our answer is 10 in base 12. Right. We are going to put a 10, 0 here, and we're going to carry, right, the 1. Right. That means in this next line, right, it's going to be 6 times 3, but we have to do one other thing. We're going to add 1. It's going to be 6 times 3, which you really must do first, plus 1. All right? So 6 times 3 is 18. 18 plus 1 is 19 in base 10. What is that in base 12? Right. Let's compare this to these values again. 19 is less than that, can't use it. 19 is less than that, can't use it. But 19 is greater than 12. So we would, in this case, do this. 19 divided by 12. How many 12s can you squeeze into 19? 1, which is 12. And the difference is 7. And then you keep going until you've exhausted all powers of 12 here. So you go to the end. A lot of times, I admit, I make mistakes a lot of times, and I forget to go, I got a satisfying answer. So then you forget to go to the next one. Don't do that. All right. Let's see. 1 goes into 7 exactly. 17 times. All right, 7 times, which is 0. We're using 1 and 7. Okay. So that's what this is equal to in base 12. All right. Put a 7 here, and then carry a 1 again. Okay. And now the next one is 3 times 8, or 8 times 3 if you like. Alright, but do the multiplication first and then you would add 1. Alright, 8 times 3 is 24, plus 1 is 25 in base 10. What is that in base 12? Alright, once you get a pattern going, you might be able to speculate by, counting. But I'm dubious about doing that. This figure, 25 base 10, compared to these, you're going to start a little bit higher, right? No, that's about the same. All right, 25 is less than this, can't use it. It's less than this, you can't use it. But it is greater than that. So we will do 25 divided by 12. 12 goes into 25 twice, which is naturally 24. The difference is 1. Save that. Next value is 1. 1 goes into itself 1 time. And it terminates. Good. So you have the value of 21. Okay. So what goes in here? We'll run out of space, so we're going to put 2, 1 in those particular boxes. Okay. Now remember, when you do traditional multiplication, right, when you get to the next, when you're trying to distribute the next value, you need to establish a placeholder, right? If there was in theory a third digit, you'd have two placeholders. What I would do is either put an X here, so just know that you're not going to put a number there, or draw a 0, which is what I was taught as a kid, all right? But I like to sort of overkill it here, make it really obvious. The X-Men are multiplying here. And you're going to start from here and fill in these voids now. Okay. So let me free up some space. Let's see. Now it's going to be 5 times 4, which is 20 in base 10. What is that in base 12? Let's see. 20 divided by 12 is 1. The difference is 8. So it'll be 18. So we would put an 8 here. And then, carry the 1. Coincidentally, it's above the 1 that was already there. Just realize that when you do 5 times 6, do the multiplication first, and then add that blue 1 here. So 30 plus 1 is 31, naturally. 31 in base 10, what is that in base 12? You would end up doing the same division. 31 divided by 12 is 2, which is 24, the difference is 7. And then you have 7 divided by 1, which is 7. So this should be 27 in base 12. Again, you carry, this is what we're adding, right, in the base. So you're going to put a 7 here, and then put a 2 above this 8 here. And now for this last part, as far as multiplication is concerned, 5 times 8 plus 2. 40 plus 2 is 42 in base 10. What is that in base 12? You're going to do 42 divided by 12. 12 goes into this 3 times, which is 36. The difference is 6. Save that 3. 6 divided by 1 is 6. And we're good to go. This is 36 in base 12. So we will put a 6 here and a 3 here because we have run out of space. It's good. Okay. Now, even though we did the hard part of multiplication, now we have to add in base 12. Yay. Alright, so that should be no sweat at this point. Just look at the amount of experience that you have accumulated, acquired. Right? Just realize that this is base 12 added to base 12. We're going to pretend that we're adding like we normally would. Right? There really is a void here, so it's just 0. You could skip even worrying about that. Then it's 7 plus 8. Right? If you did traditional 7 plus 8, you would get 15 in base 10. What is that in base 12? This figure 15 is greater than 12, so we can't divide by that. I'm sorry, we're definitely going to do that. It's less than 144, we can't do that. But we will divide 15 by 12 and see what we get. 12 goes into this once, which is 12. The difference is 3. 3 divided by 1 is 3, you get 13. All right. Just 0. So this should be 13 in base 12. Okay, so we are going to put a 3 here and carry a 1 here. And now for the next one, it's 1 plus 1 plus 7, which is 9, right, in base 10. All right. What is 9 in base 12? It should be exactly the same, because look what would happen even if you verified. You can't divide 9 by 12 for all intents and purposes. The exception of having a smaller figure would be 0 itself, but it's too small, all right? 9 by comparison, all right? So you're not going to divide by 12 to begin with. What you're going to do is you're going to divide by 1. And 1 into 9 is exactly 9. You're out of digits. So 9 is 9. So you put a 9 here. And then this next one is 2 and 6, which is 8 in base 10. One could assume this is going to be 8 as well, for the same reason that 9 is 9, because you're working within the character set here. You could verify again. If you divide by 8, you're only going to get 8. All right, so you get 8. And then you are out of digits here. All right, so you just carry down this 3. All right, so what is your solution? This is 38,930 in base 12. Okay, rather tedious, but not impossible. Okay. Alright, now I can speed it up. Alright, now we finally got into chapter 12 here. Pardon me, the 11th question. This is section 6, chapter 6. The tedium is over. This is just an example of distributing. Right? There's some shortcuts that you can employ if you'd like. We could do it brute force. Right? For the sake of time, I'll just do it. I'll do it brute force. Someone looked at me. This is really 3 over 4, and this is really 2 over 3. Right? Before you attempt to switch things around, that is, before algebra. Right? Simplify using just arithmetic. Okay? So when you see something in parentheses that you have, they're not like terms. This is an x and this is a 5. You can't actually subtract them. The best that you could do is to get rid of these parentheses is by distributing the outside content to each of the inside contents. All right? What do you end up with? You would end up with 3x over 4. It's the more or less like a top times the top there. And then 3 times negative 5 would be negative 15 over 4. All right. On the opposite side, again, you can't really make heads or tails of 3x minus 4 by itself. But what you can do is distribute this to each of the contents. Right? The effect of what's going to happen if you have a 3 here and a 3 here is that there's going to be cancellation. Right? Which means that for the first term, there's no denominator. For the second one, it remains as a 3, right? This cancels this in this particular part, all right? You could write it, if you'd like, as 6x over 3, right? Just if it makes you feel more comfortable, all right? But it will simplify down to 2 eventually. Now, 2 times 4 would be negative 8 over 3. All right, this is more or less the brute force way of doing it. There's nothing wrong with that, but there are alternatives. Right? The alternative would be to eliminate the denominators to begin with by multiplying each of these quantities by 12. Right? That will make everything larger, but proportionately, and you will get an answer that is okay. The expressions will be equivalent. to the original expressions. All right, it's legal is what I'm getting at. Anyhow, this is what you may go with if you're doing a brute force. All right. I would reduce this to 2x at this point. And now we're going to start swapping sides. We're going to bring things that are x from here over to here, and things that are not x from over here to over there. All right. So 2x is going to be integrated with 3/4 here. This is like 2/1 if you wanted to simplify it. In order to combine things on this side that are the x portion of this, remember, in order to justify moving something, if this is a positive, to move it from here to here, you'd have to subtract. All right. So whether you left it as 6/3 or you simplified it first, as I did, all right, this would cancel on purpose, right? Because it's now over here as a negative. You got to get the letters alone on one side. You get the numbers without letters on the opposite side. That's the name of the game. All right. To actually add or subtract, you'd have to get this to be an equivalent fraction now. I'm putting a 1 here just to make it a little bit easier. All right. To make it upgrade it more or less to a matching 4. So if you change this to something over 4, it would be 1 times 4 and then 2 times 4, which would be 8x over 4. 8x over 4 is the same as 2x over 1, which is the same thing as 2x, which is the same thing as 6/3. It's just it's disguised, more or less. All right. Now, if this is a positive 3 on top, and this is a minus 8 on the bottom, one of each, you subtract them, and you get a negative 5 as the top numerator here, with an x attached to it. And underneath it, the common denominator is just 4. Save that. Okay. The other portion of this is dragging the 15/4 from here to here. So you're going to do that via opposite operations, which means you're going to add 5/4 to justify canceling. And if you did that here, you're obligated to do that here. So 15/4. Right? You have the same issue where you can't really combine them. You could use a calculator if you'd like to. There's a button on your calculator that looks like this, ABC, which will allow you to implement input fractions if you like. But here it is again, brute force. The common denominator of these two would be 12. So you'd have to change both of them. They both get morphed here. 4 times 3 would be 12, so 15 times 3 would be 45. 3 times 4 is 12, so 4 times 3 is negative 32. Okay. So you have negative 32 and positive 45. One of each, you actually subtract them, you get a positive. All right. And on this side, what's the difference? It's 13. You get positive 13 over 12. All right. Now, to isolate x, you multiply by the reciprocal of 5/4, which is minus 4/5, cancels. This becomes positive overall, just x. And now you do the same thing here, times negative 4/5. You can, if you want to, multiply brute force top times top, bottom times bottom, and then simplify after the fact. I would always encourage you, try to look for relationships. It would be good if you know your multiplication tables for that reason. Simplify before you multiply. Right? So, for example, the relationship between this number above the line here, 4, and this number below the line here, 12, is that they're both made of 4. So 4 divided by 4 is 1, and 12 divided by 4 is 3. Right? That is as much simplifying as you can get away with doing. Now, it is positive 13 times negative 1, which means that x is equal to negative 13 on top. And now it's left over 3 times left over 5, which means that it's 15 on the bottom. That's as brute force way of doing it as possible. You could use a calculator. There's another strategy of eliminating the denominators entirely, but you're going to get big numbers, and that's going to be the end result no matter what. Okay. Negative 13 over 15. Okay. Now when you have these two word problems, it's going to incorporate algebra. This is an exercise in translating something that is verbal into something that is purely symbolic. All right. the mention here of simple interest means that you're going to borrow this formula PRT. Right? That's principal, fancy way of saying original amount of money. Rate, which is a fancy way of saying the percent. And T is time in years. Right? Always. Right? If they gave you months, you'd have to convert it to a fraction of so many years. Okay. Ernie deposits $2,500. That's the original amount at 6% interest. So you can multiply by 6% for 1 year. This times this times this. How much interest is earned? And then there's a second portion to this would be, what would be the total account balance, that is the interest plus the original amount? There's another formula in theory, but you can intuit this. A is equal to P plus I, right? That is, the account value is equal to the principal plus whatever the interest as a dollar value is, all right? What I would do, right, is write this in the style of fractions, believe it or not, because when we're talking about money, oftentimes it's things that are, if you're borrowing, it's a figure that's around numbers, so meaning there's zeros involved in it. So this first figure is 25/1 times 6% in the style of a fraction is literally 6/100. And you'll see what the advantage of that is in a moment. And then 1 is just times 1, so you can make it 1/1 if you like. All right, we'll just leave it alone. The advantage to doing that, if you feel comfortable with fractions, is that you can simplify again before you multiply. If this is 100 and percentages will always have 100 as a denominator, you could reduce this immediately, cross it out entirely, replace it with 1, and then switch this to just cross out those 2 zeros, and you have 25. All right? So then it's just 1 times 1 on the bottom, which is 1, which is superfluous, you don't even need it. And then it's 25 times 6, really, which is 150. So, what is the interest? The interest is $150. All right. What would the account value be? It would be $2,500 plus 150, which is $2,650. Okay. For this problem down here, so I don't have to choke here. This is an inequality problem. I think I'm gonna not use glue because it's so sticky. It doesn't want to go away. I don't know what I did with that on the pile. Oh, there it is. What about this one? Oh, that works all right. I have some very old markers here that I dug up out of storage. That works very nice. We'll go with that one. All right. Translate this again. There's 2 plans here. All right. Chris could be paid in one of 2 ways. Imagine that you're allowed as an employee to choose how you're being paid. All right. There's plan A and there's plan B. All right. And it's based upon a number of sales. All right. This person works on commission apparently. What amount of sales, all right, is Chris better off? Better off is an English phrase that is implying, since this is about inequalities, a situation where it's greater than one thing is greater than another. All right. For what amount of sales is Chris better off choosing plan A? So this first thing is plan A greater than plan B. Right? We need to establish this symbol, right, instead of an equal sign, because we're comparing 2 things, right, as more or less, right? And what I'm going to do is going to translate the description of A here in relation to the symbol, and then translate the description of B in relation to this symbol, all right? Plan A is described as Chris being paid a salary of $310 per month, right? So that would be this to begin with. $310 per is this line, and then you would have a month here. Right, 1 month. You could leave it as 1 if you'd like. Plus a commission of 9% of sales. There's still this symbol here. And now I'm going to squeak in the description of B on this side of it. Plan B is, I'll use black, $556 per month per 1 month. Plus a commission of 3% of sales. Don't feel bad ever if you, when you're trying to form an equation, or in this case an inequality, if you start out half verbal, half symbolic, mathematically speaking, right? What you'll do is you'll slowly whittle it down into the essential, right? But do what is intuitive first, right? So this whole side in blue here is A, and this whole side that you see here in black is B. Right? And that's the symbol that is in between them, just based upon this phrasing better off. Right? All right. Now, a couple of things. If you wanted to generalize this over the long haul, right, it would be, this is a rate, right? Whenever you see per, right? And this is correct as it's written, 310 line 1 month. You would have this times a certain number of months. So you might abbreviate that as, you know, per 1M, right? The months would cancel, but the word month would cancel, but you'd be left with the figure, okay? An abbreviation for sales might be S instead. So you'd have S on both sides, and you have M's on both sides. Don't worry about the M's, they're going to simplify out in a moment. Right. Let's shorten this a bit. When you have 9% of sales, it's probably easier to think of this in the context of a decimal rather than a fraction in this particular case. 9% is 0.09 as a regular ordinary number. Of means times, all right? And if it's 0.09 times S, you could make this ultra concise as 0.09S, right? And it's understood as being multiplied. On this side, again, 3% is really 0.03 of is times, and then if you just slap everything a little bit closer together, it's 0.03S, right? Slowly whittle it down into its essential. I'm gonna write a cleaner version of this because it's getting messy above here. What I have established is basically this. 310 per month, would be multiplied by a certain number of months, right, that the person is working, plus 0.09 times S. That's one side of it, and that is plan A, which we're hoping to calculate this for when the situation A is greater. And then on this side, you see $556 per month times a certain number of months plus 0.03 times S. Okay. Now, you notice that we technically have two variables here because we have months involved here. But if we're not concerned about time so much as we're concerned about amount of sales, let's make a control of this. All right, the situation here and here in terms of time would have to be the same. That would have to be consistent on both sides of the symbol, right? So do the easy thing. Let's just pretend that this is 1, all right? That would make it $310 flat because it's 1 month's worth of time. And over here, again, if you insert 1 here in place of this variable, technically, then it's $556 flat on this side. Now you don't have to worry about it, all right? Consistency, all right? We're just analyzing sales, really, so we're going to make the conditions for time the same on both sides here. All right, that leaves us with this. 0.09s is now the only variable, greater than 556 plus 0.03 times s, the only variable here, right? As with all algebra problems, we have to get it to a situation that it is the letter exclusively on one side, not two, and the numbers without letters exclusively on the opposite side, whichever you choose. My conditioning is to do it this way. Make a little table to establish sides. All right, leave a little gap here. I'm going to bring the things with letters exclusively over to here. All right, and the way that I justify doing that is by opposite operations. What is the opposite of adding? Subtracting. So I'm going to take the whole kit and caboodle, that is the number and the letter attached to it. It's ugly, and I don't know what S is yet. It doesn't matter. Something minus itself by virtue of sheer logic alone cancels out of existence, and then you plop it here underneath the thing it most closely resembles. All right? Why? Because we're going to merge this. All right? But you perform opposite operations to justify moving over the symbol. That's algebra. All right? At the same time, for the sake of space, if I'm going to establish letters over here, then numbers without letters must go over here. There's no sign here, but one would assume it is a positive. No one likes to get paid in negative money, right? And then you would subtract 310 to cancel it here, and then justify that way, moving it over here. 310. All right, what does that leave you with? It leaves you with 9 minus 3 essentially is 0.06 with an S attached to it. And it's a positive overall because of the larger magnitude positive. Right here. This is oriented as greater. And then you do the arithmetic on this. This is a 6 left over, this is a 4 left over, and that's a 2 left over. 246. Last thing is move 0.06 back the other way because we're going to isolate the S, the number of sales. So how do you do that? Opposite of multiplying to justify moving this from here to here is to divide. There's a cancellation effect here, be 1, right? And then S would be greater than the outcome of 246 divided by 0.06. So we end up with what you should get is $4,100. $4,100. Right. So, for what amount of sales is Chris better off choosing Plan A versus Plan B? For sales that are greater than 4,100. Right. If it was exactly 4,100, they'd be even, right? You get the same figure here and here. If you have something bigger than this, then this side will start to be greater. Okay, the Plan A situation. All right. Now we're at 2 hours, so I'm going to try to go a bit faster. Because even if I make a 3-hour video, I know from experience the upload time is going to be astronomical, so let me go a bit quicker. That takes up so much time. Let me see if I could shrink this and I could fit more stuff on one page. Okay, that looks better. All right, this is to calculate the slope using the slope formula, and you use these figures. All right, remember the slope formula is, maybe use green in this case, y the second minus y the first over x the second minus x the first. You have to take a little artistic license and decide which is the set of 1's subscripts and which is the set of 2's subscripts. So my feeling is that if this shows up in your face first, then this is x1 and this is y1. And if this follows that, then it would be x2 and y2. All right, now just be careful. There's minuses, a negative symbol in the formula. All right, so don't ignore them. Y the second would be -8 in this position, and y the first would be -1 in this position. You have a double negative in this case, which makes this -1 plus 1. Right? According to the combination of integers rules for adding or subtracting, one of each, you actually subtract to establish the digit of 7. The answer will match the sign of the magnitude of the sign of the larger magnitude. Greater distance from 0 is -8, so this is a -7 on top. All right. When you substitute for this one, all right, the x's, this is 10, and this is -5. Again, there happens to be a negative in the formula, so be careful. This is a double negative, so this is 10 plus 5, which is really just 15. Right? You should get a slope of -7 over 15. If you want, sometimes textbooks, a lot of times they will simply do this. They will favor neither the top nor the bottom. And you could write this exactly like that. Just realize that this is essentially a negative divided by a positive, which means that it is negative overall, right? So you could write it that way if you'd like, or you could write it that way if you like. Just don't put a negative in both places, because it isn't correct. Then you'd have a positive technically. All right? Now for this 15 here, you have to graph this by hand. The style of writing it that would be easier to graph would be if it was in y equals mx plus b. That is the slope-intercept form of the line equation. So that requires a little bit of algebra to rearrange stuff. If you have x plus 4y is equal to -8, then let's get the y alone on one side. That's sloppy. Move the x first from here to there. Right? It's a positive x here, so to justify moving it, it would be negative on that side. They would cancel even if we don't know what it is. Let's see if this black writes better. Yes, much better. Let's see. If you have what's left over here is 4y, and you try to conform this a little bit closer to the model of slope-intercept form, just switch the position of these. You're not playing algebra, you're really just being a twit. All right, so this is -x here, and this is -8 adjacent to it. All right, they cannot be combined because they're not like terms, so a letter is in the middle. All right, divide by 4 both contents here. Remember, you can't just do it one or the other. It has to be both things. That makes this y equals, make this look a little bit more normal, -1 over 4 with an x attached to it. Why a 1? Because that's really understood as being there to begin with. The coefficient is never 0 if it's a letter, right? It's a number, 1. Right? So it's -1/4. And then if you simplify this, it would be better to say it as -2. Right? Now, if these represent a slope, that's the intercept here, and a slope, m, right? Start with the coordinate. The y-intercept is literally where the line would cross the y-axis. This is 0 and then -2 because there's a negative here. So you're going to put a dot at -2, which would be there. All right. This is -1 over 4. Right? If it's -1 over +4, and you could switch it around if you like, that means 1 down and 4 to the right. But not from the origin, because it's not a coordinate. It involves x's and y's, granted, but it's not a coordinate. It's from this point where you left off, the y-intercept. So you can go down 1 and then over to the right 4. 1, 2, 3, 4. So you have a second dot here. And that means you have a line that basically looks like this. If you did it the other way, if you just decided to put the negative down here and the positive up on top, positive 1, negative 4, you'll end up in the same place. Right? You'll end up with the same line. You don't have to worry. All right, 1 up and 4 left. Watch. From here, 1 up and 4 left is 1, 2, 3, 4. The dot would be here. I just drew it sloppy. Yeah. I'll draw a nicer line. Be a good sport here. You really just need 2 lines, 2 dots rather, to draw a line. But this is what would look like. They're inclined exactly the same. Okay. Down 1 over 4 lands you on the line. Up 1 over 4 to the opposite direction. Left is same line. Okay. All right. Here's a system of equations. All right. Now you have a couple of choices. When you have a system, I better expand this. When you have a system of equations, you have these 3 choices. Graphing, if you had a graphing calculator, it'd probably be that is rearrange this to y equals mx plus b. Also, the other one, look for the point of intersection. Rearrange this to solve for x, or rearrange this to solve for y, and then stuff it in the other one. I think people tend to do that the most often. And then there's an elimination method. The elimination method is to basically write equivalent equations. They're not going to look the same, but they'll be consistently mutated into something else. Now, you could decide to get rid of the y's, you could decide to get rid of the x's. What occurred to me is to try to eliminate the x's just because there happens to be a smallest number involved here. Right? You kind of have to think about this as being a column of like terms. Right? And now we're going to change the appearance of this one and then this one so that we're going to try to facilitate a cancellation effect, essentially. Right. Normally, you wouldn't dare, right? You wouldn't dare blend together the parts from one equation to another. But for a system, you do that exactly. Now, what would we want if we choose to get rid of the x's, right? We need a number in place of the x's that is of equal magnitude and opposite sign. All right. The number that we would go with in the case of 5 and 2 is the least common multiple of 5 and 2. It's always the least common multiple. So the least common multiple of 5 and 2 is 10. That is, if you count it by 5s, you get to 10 first. All right, that would match counting by 2s, you get to 10, right? 5, 10, 15, 2, 4, 6, 8, 10. The first number that matches is 10. That is the figure that has to be here and standing in basically in the x column, right? One has to be positive, one has to be negative. If we want to change 5 into that, then what in theory we would have to multiply by is 2, right? You can get away with murder in math as long as you're consistent. So if you wanted this to be the effect, positive 10, you'd multiply by 2. You can only do that as long as you do it to all parts, right? So you're going to change the appearance of what you're given, but you're going to do it consistently. That's what makes it legal. 2 times 5 is 10. Then over here you have 2 times a negative 7 is negative 14 with a y attached to it. And then you have 2 times negative 44, which is negative 88. Right. Down here, it's essentially the same idea. You're going to multiply this by 2, by the number 5, right, to establish the magnitude of 10. But I'm going to be sneaky and also multiply by a negative. Why? Because I need it to be a negative to facilitate a cancellation effect if I blend these together. All right, so you can get away with this only as long as you're consistent. So negative 5 times 2 is negative 10. Negative 5 times positive 3 is minus 15y. And then negative 5 times 23 is 15 carry the 1, 115, right? I believe it is. I'm going to switch my papers again. Yeah. So on this side of equals, you have negative 115. Okay. So now you have a table, and we're going to go through the process. Right? The whole point of this exercise of changing the appearance of this equation and this equation, sometimes you only have to do one, not both of them, is to basically get the x's to cancel out of existence when you blend these equations together. So 10x, I don't know what x is, it doesn't matter, something minus its opposite sign is going to be canceled. Right? That leaves you with just y's. You've eliminated the x's and now you're left with the y's. In this case, there's going to be an amplification effect because you have both the same signs. In this case, it's going to make it a negative 29y, which is awful, but I mean, it's not too bad. All right, and then over here, same thing. Negative, negative makes a bigger negative when you add them. So this is 13, carry the 1. That's 10, carry the 1 here. 203. All right? Yeah, okay. Last thing is to divide by negative 29 here, cancels, the negatives cancel, and divide this side by negative 29. You can use your calculator, and what you should get is that y is equal to negative 7, actually. All right, let me just verify that. So I neglected to write it. 88 plus 115. Come on. Is 203 divided by negative 29, negative 7, right? Save that. What you must do, I don't have my pencil here. Oh no, you know what, I'm dope. This is a larger negative as well, so this is a positive 7, sorry. Right? A negative divided by a negative is positive, good. Okay. Now, once you have solved for one letter, you could go back to any incarnation of this, and it would be easiest to go back to the things that involve the smallest numbers, strategically, and insert a positive 7. So in place of a y, let's put 7 times 3 here, right? This makes this 2x plus 21 is equal to 23. We're going to move 21. 2x is equal to 2. Divide by 2. X would be equal to positive 1. All right, those are your two values, 1 and 7. Okay, 1 for the x, 7 for the y. Right. Essentially, this idea of implementing a system, 2 equations or more equations stacked, all right, is the strategy you would employ for doing a problem like this. The soybean mixtures, whenever you get chemistry classes, a lot of times you have problems like this. When you talk about percentages of solution, or the slightly more dry and boring question about mixing nuts. You know. Here's a strategy that has served me very well. Right. If you have 2 variables, right, to solve for, then you use a system of equations. And the way that it works is that if it's 2 variables, you need 2 equations. If you have 3 variables, in theory, you would need 3 equations, and getting into matrices and stuff like that. So you're going to have a first equation, and you're going to have a second equation. Right. The first equation, I would make it basically a composite of volumes and or weights, a percent and volume or weight type of equation. And then the second one, I would make just the volumes, just weights. Equals something. Okay? So you have something that involves percentages and the volume or weight quoted to you, and then you have a second equation that is just the volume of the weight, no percentages at all. So let's do this. All right, here's your first. Often they're tied together with a little caliper like that. Soybean meal is 18% protein. All right. Cornmeal is 9% protein. How many pounds, in this case they're talking about a weight rather than a volume, all right, should each be mixed? How many pounds of each should be mixed to make 360 pounds, that is 16% protein? All right. Let's do the harder one first. All right, you could do either one of these first, but to me it seems more natural to do the harder one, believe it or not. The thing that involves simultaneously percentages and the weight involved. All right. Let's use a letter to represent soybean, S. All right. Let's use a letter C to represent cornmeal. All right. So you have 18% of soy, right? And if we're talking about a mixture, it's more or less implied plus. You can expect that it's going to be something plus something. Yeah. Something plus something equals something. 18% of soybean, all right, 9% of corn is, if you see the word is, you can assume it is an equals, all right? 16% of, in this case, the mixture is just described according to its weight, 360 pounds, LDS. Okay, that could be whittled down, all right, a little bit further. All right, but that's the first basic equation, right? The second one is the thing that is just the weights of stuff, right? So we don't know, right, because the question is asking us how much weight, but how much soy plus how much corn would be equal to 360 pounds total. Notice that in this case there are just the variables for those weights, the weight of this, the weight of this, independently, and the total weight. All right, so we're ultimately solving for S and we're solving for C, similar to the last problem that you're solving for X and you're solving for Y. They're just labeled differently. Now, what I would do is go back and, make this a little less ugly. Right? It's 18% of the weight of soy. It's 9% of the weight of corn. Right? And then it's the total is 16% of 360 pounds would be protein, naturally. All right. This can be reduced to its decimal equivalent. 18% is 0.18 with an S attached to it. 9% is 0.09 with the C attached to it. And this would be equal to 0.16 times 360. That's the thing that you could actually reduce to a number. Right. Which makes, there's my marker. Which makes what? This is now the reduced form of your first equation, so I'll erase the junk that is above it, make it less distracting. And if we straighten this out, 0.16 times 360, you should get 57.6. Okay, 57.6 pounds. Just like this is, in theory, 70 pounds. Now, because you have this blue equation is basically coefficient of 1 here, which we don't bother to write, coefficient of 1 here. The method for solving this, I would not use elimination. In this case, I would use substitution. Substitution means rearrange the parts, either S isolated to one side or C isolated to one side, so that you're solving for either soy or corn. All right, I'll just move the C. All right, if I wanted to justify moving the C from here to here to solve for S, it's not immediately satisfying, granted. I'd perform the opposite operation. The opposite of adding is subtracting. Alright? And I'm going to subtract c here. That cancels the c's here, and now I have this third equation, which I'll put a little asterisk next to it, as s is equal to 360 minus c. That may not seem like much, but what you can do is now take this and stuff it in the red equation where the s is. I'm short on space, so I'm going to erase a little bit. And in place of this s, I'm going to tuck the half of this that is what it's equivalent to. 360 minus c times 0.18, and this is plus 0.09 with the c attached to it is equal to 57.6. Just to make it less complicated. Okay. If you distribute 0.18 times 3.6, what do you get? You get 64.8. And then this is minus 0.18 with the c attached to it. There's this plus 0.09c. These are like terms, which means that these things can be combined. My red is dying. And we're going to straighten that out. Again, I'm short on space, so I'm going to put this here. $64.8. The difference here is negative 0.09 with a c attached to it, and on the opposite side it's 57.6. Now you have an algebraic equation. It's a little uglier than normal because you have decimals rather than whole numbers, and the letters are less familiar to c and s's. But this is exclusively c, which means that you could solve for corn, ironically. All right. So you make a little table, you move 64 over here, minus 64.8 to minus 64.8. You're going to get a negative, but don't feel bad. What do you get? You get negative 7.2. And then there's this negative 0.09c here, which means what? It means, again, I'm erasing this just for space. You would divide by negative 0.09 here to cancel, and then do the opposite here. Right. A negative divided by negative is a positive, so your c value will be positive as it should be. The relationship is the same as 129 is to 720, which is 80. Right. So 80 pounds, right, of corn is what you would have. Right. If you then go back to the rearranged second equation and you put 80 in here, right, that will tell you what the balance would have to be out of 360. The soy amount of this would be, let's see, 280. 280 pounds. Okay. The best strategy I could tell you is exactly what I said. All right, two variables, you need a system. If you're doing them at the same time, make one equation just whatever the volumes are quoted to you, or the weights is in this case. Make a second equation that involves both the volume and the percentage, or if you're talking about weight, the weight and the percentages, right? And they're usually a sum, you know? So start out with just assuming that you're adding two things, especially if you're talking about a mixture. Okay? That has served me very well in my life. Moving on. Alright, shrink this so I can get more done. Alright, these two, 18 and 19, you have quadratic equations. Quadratic equations are degree 2. That means the highest exponent is 2, and they're arranged ideally set equal to 0. Right? If they're arranged set equal to 0, then the technique for solving them would be either one or two things. Either you're going to try to factor and then use something called the zero product rule, or go for the bazooka, which is what people often do, right? The formula, the quadratic formula, right? This is like swatting a fly with a bazooka, though. Sometimes it's not necessary, all right? When you do something like this one, de facto, all right, you might be tempted to, because of the numbers are rather large here, you might be tempted to use the quadratic formula. It would work, all right, but it might be more trouble than it's worth. So the method for factoring here, I would call it AC product pairs, all right? 3 times 32 is 96. What we would have to do is to figure out pairs of factors that make 96 in order to help us factor this first. All right. Start with 1. All right. Start with always the easiest. All right. 1 and the number. There's 2 pairs of factors. All right. This is even, so it would be 2 times something, and that turns out to be 2 times 48. It came from 3 times 32. It is divisible by 4 if you check. Right? 4 times goes into that twice with 1 left over, 24. It doesn't end in a 5 or a 0, so you can't use 5, but you can use 6 because 2 and 3 work. 6 goes into this once with, let's see, 3 left over, 16. And you should check with 7. It's not going to work with 7, all right? But it would work with 8. Right? There is technically another pair of factors. Now you might wonder naturally, well, how do I know when to stop? Jesus, this is busy. 12 times 6. Part of, not to make a speech again, but part of the reason why you should definitely teach your students to memorize their multiplication tables is because this would be less arduous if they had that frame of reference. So I'm sorry to say, if someone ever told you, I don't memorize the multiplication tables, they're damn fools, all right? Because now they've hobbled a person from doing this, all right? Anyhow, we can't change the past, we can only affect the future. The other way of doing this is to incorporate rules of divisibility. You heard me say that this was even. So I know it's got to be 2 times something. All right, and now I checked to see if this was ending in a 5. That's how I knew it couldn't be 5. The rule for 6 is that if it has factors of 2 and 3, then it has a factor of 6 as well. This is all of them. And you know when to stop because you notice how far away you start with and how close you get, right? Eventually you will get to a point where you would maybe overshoot them. If you decided to check 9, it wouldn't work, all right? You'd get a decimal as the other factor, and that's not what we want, all right? And then if you tried 10, it wouldn't work because it would either be 90 or 100, all right? So you pretty much, you've gotten as close as you can get, right, being as far away as you were, all right? So you've covered all bases, all right? These are the choices, basically, that you have to work with. Now, you might wonder, why did I bother doing this? Because what you're going to do, ironically, is you're going to take the middle number and you're going to split it, right, using one of these pairs as choices. Something plus or minus something else makes 20, all right? If you added 1 and 96, you're not going to get 20. If you subtracted them, no way, all right? You can eliminate that as a possibility. If you added these, you get 50. If you subtracted, you get 46. That's not it, all right? 3 and 32. Added them, you get 35. That's not 20. If you subtracted them, you get 29. No. Getting closer, though. 4 plus 24 is 28. That's the wrong direction, but if you subtracted them, you would get 20. So consider that as a possibility. All right, but go through the whole list here. 6 and 16 added is 22. That's too much. All right, if you subtracted them, it's even worse. The only other thing that would potentially work is 8 and 12. All right, and you should check that eventually, but what's going to happen is that you'd have to add in this case in order to produce 20 here. Eventually, when you get down into the weeds of it here, is that you would eliminate this even as a possibility because the only way to get 20 in that case is to add, and there's a problem here with a negative in it. So it's probably 4 and 24 that you're going to use. So what does that mean? It means that this 32 that's sitting here, you're going to keep it. This 3 that's sitting here, you're going to keep it. The junk in the middle is going to have a 24 and a 4 with these attached to it. And now you're going to straighten out the signs. There was a minus here, so I'm just going to continue with that. But the sign here and the sign here, I have to figure out to produce a positive 20. I do that as an afterthought. All right? If I want this to shrink 24 into a 20, the operation that causes that is subtraction. The combination of signs that causes subtraction is that you have one of each. One of each sign causes subtraction. If I want the outcome to be positive, then the larger magnitude has to be positive. And this is how I would arrange that. Now again, if you've never done this before, and I would be a little surprised because this is the end of the semester, all right, you might go, geez, why did I make it worse? It was 3 terms wide, now it's 4. Because the irony is that once you have it in 4 terms, you only have to pay attention to 2 chunks at once. And it's easier to factor this, right? Especially if you know your multiplication tables by heart. All right, again, never tell your students don't memorize the multiplication tables. That is the stupidest thing in the world. All right, again, whatever administrator, genius thought that you should not memorize the multiplication tables is a damn fool. All right, and they deserve to be slapped. All right, you could tell them I said so. You know, enough speeches. There's an obvious letter in common, so if you're factoring this, it would be V on the outside. The common factor that is a number that makes 32 and 24, because I know my multiplication tables, is 8. All right? 8 times what is 32? 4. V times V would make it V squared. 8 times 3 is 24. There's a V already there. Now what you're hoping for is when you shift your focus over to here, that when you're trying to factor these, and you can just start out by borrowing that number that's negative, you are going to basically get the same exact stuff that you see here. All right? The way that it works is that this is, again, you start out by borrowing the sign that is here, and notice that it's already 4V. The only factor that they have in common, that's not squared, sorry. The only factor that 4 and 3 have in common is 1. So that's the GCF, ironically, somewhat ironically. Negative 4 times 4, V, is negative 4V. Negative 1 times negative 3 would be positive. And we need it to be negative. So a negative times a positive would be a negative. And thankfully, the guts here and the guts here are a match. And they have to be exact. Because the way that what happens now, when you have identical features here and here, including the signs, has to be perfect. It factors like this. Right? The match gets its own parentheses, and then the other stuff that is on the outside, which I affectionately refer to as the left outs, because it's very literal, they get the second parentheses adjacent. You only have to write the match one time, right? That is actually the GCF of this entire thing, right? Anyhow, these 8V and -1, they're the left outs because they're literally on the left and they're literally on the outside of this. Silly, right? Anyhow, having done that, right, now that you have the match of 4V plus 3 as the match, and then adjacent to it 8V minus 1. What's on the opposite side of this? After all this is factored, 0. Right? You could now take advantage of a simpler truth that you kind of take for granted, any person does. There's something called the zero product rule, and what that is simply saying is that 0 times anything is equal to 0. So even if you had something ugly and complicated, if you know that this first factor is 0, then regardless of what this is, that's the outcome. Right? Even if you switch the position of these, because multiplication is commutative, right? Even if it was anything in front times 0, it would still be 0. Right? Even if it was both of them, anything times 0 is still 0. Even if it was 0 times 0, it would be 0, right? So, taking advantage of that fact, what you could do is you could basically write a smaller equation. I wish that would stop happening. All right, which is that this is 4V plus 3 is equal to 0, possibly, all right? and that this is 8v minus 1 is equal to 0. All right? And then you go through the motions of solving this algebraically. How so? You move 3 via subtraction. 4v is left over is equal to negative 3, divide by 4. V in one instance is negative 3/4. Save that. You're going to get a second answer. It comes from this. Move 1 by adding 8v is equal to 1, divide by 8. The other possibility is that v is positive 1/8. Okay? Now, if you were in Algebra 2 or maybe in pre-calculus, they'd make you check these, but you don't have to worry. Okay? That, with enough experience, becomes the go-to sort of method to solving a problem like that. I think more of a novice, and I wouldn't fault you, especially for the sake of time, and if you're not familiar, a person, when they're dealing with something like this, would go straight for the quadratic formula. Like, frick this, I am not going experimenting with anything new. All right, anyhow, what you end up with is this. All right, you compare this to a quadratic equation, and this emulates that model. This is x squared minus 3x minus 18, might be a little bit hard to see, but what that means is that a is 1, b is negative 3, and c is negative 18. All right? And then you're going to insert them systematically in the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. All right? The bazooka, right? You take positive 1, negative 3, negative 18, and then stuff them in the formula. All right? As long as you follow the order of operations correctly, and you should, all right, you'll get 2 answers. Now, the way that this particular problem would work is that you wouldn't really have to use the quadratic formula. You'll get round, nice numbers anyhow, or whole numbers. Anyhow, a 1 would go here and here. Negative 3 would go here and here. And a minus 18 would go here and here. Alright, so what does that mean? It means that to straighten this out slowly but surely, you really should just pay attention to the inside guts of this. That would really be where your attention should be drawn immediately. But you can get away with tidying up the outside because it doesn't really have any bearing on it. Alright, a double negative for the b value is just regular 3. And plus or minus is in the formula. And then the guts of the square root are the following. 9, because it's negative 3 times negative 3, plus 4 times 18, which is, let's see, 32 carried through 72. And the whole thing is sitting on top of 2. Right? Again, if you follow the order of operations, you really should just be paying attention to the discriminant here, is what that's called. And deal with that first, crunch that down, but you can get away with simplifying that and that as well. This is now going to be 3 plus or minus the square root of, what's 9 plus 72? 80 over 2. You can factor this. Oh, I'm sorry, 81, what am I saying? Stupid. 9 plus 72 is 81, which is why it works nicely. The square root of 81 is 9, so this means that you're either going to add 3 plus 9 over 2, or you're going to subtract 3 minus 9 over 2. Right? When you have quadratic equations, that is degree 2, the highest exponent is 2, expect 2 answers, all right? Even if it's the same number twice. All right? 3 plus 9 would give you 12, which means that this is 6. Positive 6 is one possibility. Right? In this instance, you get negative 6. Negative 6 divided by 2 is negative 3. Right? Those are your 2 answers, positive 6, negative 3. All right, now, this thing down here, use the vertical line test to determine whether the graph represents a function or not. Functions are, for every x value, there is only one y value. That's the formal definition of a function. But if you wanted to check with a graph rather than analyzing the actual coordinates, what you can do is draw an imaginary vertical line through this. If there is more than one point of intersection, then it is not a function. What that means is that for an x value, there's two different y values. All right. This is the point of intersection. This is the second one. All right. So even for that first try, you could do it several times if you want. And you should be more thorough because sometimes things are not as obvious. All right. There's more than one intersection, so it is not a function. Right? It does not pass the vertical line test, an imaginary vertical line drawn through the actual graph. Right? More than one intersection, it fails. All right. Okay. Okay. I put these little diagrams here if it will help you convert from milliliters to liters. All right. In this case, kilograms to grams, or decigrams in this case. Just beware. All right. Let me zoom in a little bit, maybe. You, after doing enough of them, especially if you've been in a science course, you kind of do things intuitively after a while. But if you need the scaffolding here, remember the base unit in this case for volume would be liters. So that'd be on the middle. And then the smaller things would be to the right side of it. So this would be deciliters, centiliters, and milliliters. Right. I'm using capital L's because that's what I was taught. Over here it will be increasingly larger units, decaliters, hectoliters, and kiloliters. Yes, some of these don't get used too often, but that's how it would be arranged. Look where you're starting with, milliliters. All right. Starting here, and you're going to standard liters. How many jumps would it be from here to there? All right, 3. So that means when you take a number 9.55, in that same direction, you go 3 jumps. Make 3 waves. 1, 2, 3. Fill in the void with the appropriate number of zeros, their placeholders. And that would be your value. 0.00955. You can put a 0 up in the front, but it's just for stylistic purposes. A similar thing here, but you're starting from different places. The units are grams, so that would be in the middle here. This would be decigram, centigram, milligram, like a vitamin. Then decagram, hectogram, and kilogram, which is more normal. All right. You are starting at kilograms, that's the given number. So you put a dot here. Right, and you're converting to decigrams, dg. So how many spaces is that? 1, 2, 3, 4 in that direction. So you're taking the original number 117. If it's a whole number, you would assume decimal point starts there, and then make 4 waves. 1, 2, 3, 4, and fill in the void with zeros. 0, 0, 0, 0. Every 3 in the United States, we put a comma on this side of the decimal. And that's the figure. 1,170,000 kilograms is, 170 kilograms is 1,170,000 decigrams in theory. Okay. Moving on. This one you could reason, you can memorize stuff, but you could also talk yourself through it. And I would save this information for a latter problem anyway. How many times larger is a square kilometer than a hectare? A hectare is a lesser known unit, which is really a square hectometer. All right. If you have already established, right, that you have decameters, hectometers, and kilometers in respect of each other, how far apart are these two? All right. Just one jump. Right? If jumping on the scale basically amounts to moving the decimal place left or right, that's different powers of 10. One jump is 10. It is either multiplying by 10 or dividing by 10. Right? Anyhow, draw, and if it helps, draw an actual, just a little square, literally, like this. Alright, here's a square kilometer, which means its dimensions would be 1 kilometer this way, and 1 kilometer this way, right? Figure out what is 1 kilometer onto itself, right? Hectometer is the unit, that's not a hectometer is the unit just adjacent to kilometer. Right? And again, it's just a difference of a magnitude of 10, basically. 1 kilometer is 10 hectometers. Right? So this dimension would have to be 10, and this second dimension would also have to be 10. If we're talking about a square kilometer, right, or a square hectometer, right, then we're talking about an area. And you know the formula for area, right? It's length times width, or it's side times side, if you like it, square terminology. All right, so it's just this number times this number. All right, so 1 kilometer squared would be equal to 1 kilometer times 1 kilometer. But if that's really 10 hectometers each, what is that? What's 10 times 10? 100 hectometers squared, which is 100 hectares. Same difference, same product. Okay. So it's 100 times greater to answer in the way the question is asked. In this instance, this is 100 times greater. Convert 10 cubic meters to so many cubic centimeters. This would be practical to draw, again, an illustration. If we're talking about something that's cubic, we're talking about a solid object that is literally a cube, and therefore it has a volume. Here's a cubic meter. That means that its dimensions, since it's a cube, have to all be the same. So 1 meter this way, 1 meter this way, and 1 meter this way. A volume would be a length times a width times a height, right? And it would be 1 meter times 1 meter times 1 meter. But let's figure out how much is each individual meter worth in terms of centimeters, right? On the opposite side of meter would be decimeter and then centimeter, right? It is a given, you're making 2 jumps in this case, that you would either multiply or divide by 100. So the relationship is 1 to 100. 1 meter is 100 centimeters, right? That's something a person would intuitively know if they had a meter, right? 100 here, 100 here. So instead of multiplying 1 times 1 times 1 to get 1 cubic meter, what you would have to do is multiply 100 times 100 times 100, which means what? Centimeters, centimeters times centimeters. 6 zeros would be this, right? For 1 cubic meter, right? 1 cubic meter is 1,000,000 cubic centimeters. There's one little caveat here that we have to satiate here as well. I need to erase this just for the sake of space. We figured out the relationship of 1 meter, a cubic meter, to 1,000,000 cubic centimeters. What if you had 10 times as much, because that's the original question, 10 cubic meters? It would just be this number times another 10, which would make it what? 7 zeros. 10 million cubic centimeters. Okay? Draw pictures, it definitely helps. For 25, find the area of the blue shaded region. All right, here's the formula. Think of this as a donut hole, all right? If we're gonna find the blue shaded region, we're just finding the walkway that is around this shape here. All right? But in order to do that, the area of the blue would be equal to the area of the whole blue just blue, minus the area of the orange in this case. Okay? Now, if this is a uniform walkway, this dimension of 1.4 would be the same all the way around it. And the reason that is important is because if we wanted to get the total length across this, it would be 1.4 plus 23 plus another 1.4 that way. And in this instance, it would be 1.4 plus 8 plus 1.4. And in that case, what do you get? 25. Area is, if you can imagine, the whole entire area without the hole in it. There's where English gets you in trouble, right? Whole is an entire, and whole is in, there's a void, you know? The whole blue is in the entire blue, right? Without whole, would be the length of it times the width of it, right? Well, the length would be 25.8, right? 25.8 times 2.8, 10.8. 10.8 that way, right? These two things multiplied would give you the area as if there wasn't the orange thing in the way, right? The orange thing is a length times a width as well, which in this case is much simpler. It's 23 times 8. Which is what? 184. What you end up with is this: 278.64 for this, minus 184 for this. Right. Subtracting these two leaves the ring that is the walkway. Right. And in that case, you should get 94.64. Alright. In terms of the units, you really should check the whole meters. If we're talking about an area, it would have to be meters squared. So 94.64 meters squared. Okay. These two are pretty easy. They're just using the formulas that are there. You're going to convert Fahrenheit to Celsius, and in this case, Celsius to Fahrenheit. Notice that there, in this case, the Celsius formula, there's a parentheses though. So when you insert this value of 89, make sure that you do the subtraction first. 7, and that's 57. All right. You end up with this: 5/9 times 57, technically over 1. There's no getting around it. You can't really simplify it up front. So you do this times this, and this times this, and you get what? 35. 285 over 9. If you divide 285 by 9, what you should get is, it's going to end up being 31 2/3, so round it approximately 32 degrees Celsius. So that's actually quite hot. Over here, when you input 20, you have to do the multiplication first. There's no parentheses. You can simplify this up front. 9/5 times 20/1. Simplify. It's really 9 times 4, which is 36, plus 32, which is 70. 68. 68 degrees Fahrenheit. So 31.6 repeating is about 32 degrees Celsius, and 68 degrees even would be Fahrenheit. Good. This one, this is unit conversion, but between different, also metric in this case. Is just the slightly less familiar unit of a metric ton here. Okay. Given the volume of water is 2,304 cubic meters, use the reference table here to convert to mass in metric tons, all right? Because of the definition of a meter, the relationship between a meter, a cubic meter, liters and grams, you can convert to what is a volume into a mass actually. All right. When you're getting down to it, 1 cubic centimeter is equivalent to 1 milliliter, and that would weigh 1 gram by definition. All right. So there's probably more than one way to do this, but the way that it occurred to me is to borrow that system. All right. What you're given, you're going to multiply by conversion factors. Now, this may take several conversion factors, but eventually that will spit out is what you want. So, we're given 2,304 meters cubed. So what we need to do is to figure out, well, what can we convert this to? Do I have cubic meters? I don't. I have cubic centimeters. Right. I did take the time earlier, though, from that earlier problem, to figure out that 1 cubic meter is equal to 1 million cubic centimeters. So if you did that problem, you have a conversion factor already, and you can put that in here to convert this to cubic centimeters, which can be converted to grams. All right. So 1 cubic meter, because we did the earlier problem, we know we can establish this conversion factor is 1 million cubic centimeters. Right? That will get me so far as cubic centimeters. What I would end up doing eventually after that is then multiplying by yet another conversion factor. A conversion factor that would change cubic centimeters, in this case it would be 1,000 cubic centimeters, into so many grams. It's 1-to-1 relationship, so it's 1,000 grams. All right? You may or may not know, all right? There's a relationship between grams and kilograms. 1,000 kilograms, pardon me, 1,000 grams is 1 exact kilogram. So we have a third conversion factor here. And then it just so happens that this is the relationship to metric tons down here. So we'd have another one. The fun part of this, when you develop a level of comfort, and it may not come immediately, but it does eventually, I promise, is that you think about this as a machine, that you're setting the controls in the machine, right? And then you have the satisfaction of crossing out a lot of stuff. 1,000 kilograms is equal to 1 metric ton, NNE. So you could use the abbreviation of lowercase t. Standard tons in the imperial system is a capital T, and we spell it T-O-N, at least in the United States. All right, now the machine is rigged to go. All right, it's more than one conversion factor, but the relationships, which I could have switched around if I needed to cancel in a different way, are all set to go. All right, this is above the line technically, the given thing. You can put a 1 here if you like. And this is below the line. Because I've strategically arranged these relationships, these numbers, as I have, I get the satisfaction of doing this. This will cancel this eventually. The cubic centimeters that are left over will be canceled by this cubic centimeters here. The grams that would be left over will be canceled by this gram, and the kilogram here will be canceled by this gram. Then there are the numbers as well. They're all nice round numbers. So you could use shortcuts if you feel comfortable, all right? this would just be brute force multiplication here and here. But rather than do that, and you can, it would work. If you just did all the tops times the tops, and all the bottoms times the bottoms, and then divided whatever the top is by the bottom at the end, you will get the answer. But use shortcuts, be strategic, right? There's 1,000 here and it's 3 zeros. So you can eliminate 3 zeros out of that immediately. And as a matter of fact, there's another one. You can do it again, you know? The zeros that are in here, all right, can knock off the rest of these, all right? All right? And then there's another one here, all right, which would affect that one if you'd like. You know? So these 3 zeros would eliminate these 3 zeros. And look what you have, really. You have 1 times 1 times 1 times 1 times 1, which is superfluous then. You don't even need a denominator. It would technically be a 1 on the bottom here. The unit is already arranged to solve for metric tons, so that is already where it's supposed to be. The top would be 2,304 times 1 times 1 times 1 times 1, which is just 2,304. I stole this question from my lab. Because I wondered if maybe you wanted an explanation as to why it ends up being that way. Anyhow, this is the reason. It kind of takes you down a path that you end up going back from, all right, in terms of the numbers involved here. There's a lot of cancellation, all right? Any way you slice it, you're going to get that as the answer. This is another problem I stole from my lab. Is I kind of felt it was a little unfair that they asked you this, as it assumes that you know some stuff that you might not. If you've never taken a physics class, you might be baffled by this question, but it isn't too bad. It's actually very satisfying. All right? And here's the logic as you would maybe talk yourself through it, even if you knew nothing. All right. Determine the quantity of mass here on this side of the seesaw that would be needed to perfectly balance this seesaw. All right. Notice that this is the fulcrum here, the lever here is a little bit longer than this here. All right. That this is heavy. A couple of things. All right. If something is balanced, to use the word balanced implies that two things are the same. This implies that something is equal to something else. Right? What is the something? In this case, it's actually what, if you wanted to be technical, it would refer to a torque. The torque on this side of this problem. And then there would be another torque on this side. They have, torque is not quite a force, it involves a force, but it's a lever as well. All right? So there's the torque on the left of this point, the fulcrum, and there's the torque that is on the right. Now, technically, you don't really need to know about it. To me, it would make a person much more comfortable, all right, with this explanation. There's a problem, and this is the formula. A force that is a weight here multiplied by a length. All right? And then on this side, there's a force, it's a different one, and a different length. All right? What is the force? The force is weight. Weight is a downward pointing force due to gravity, right? All right? A force is really dependent upon two things. All right? It's a mass times an acceleration. All right? They only tell you the mass, all right, in this case. But the other side would have to be the exact same factor. The acceleration here would have to be the acceleration here. Now, as a technicality, what that means is that the masses are going to be different, right? And the lengths evidently are, but in order for these things thereafter to be truly balanced, truly equal, this factor, that is the acceleration due to gravity, which would be 9.8, is actually irrelevant, because it would be the one thing that has to be the same on both of these sides. Again, if a person took a physics class, they would be okay with that. All right, but I'm here to tell you that's what would happen. All right, this factor would be canceled by the same exact figure on the opposite side. And since it's just involving multiplication, if you wanted to play the game of algebra, you would divide it to cancel it. All right. So what are you left with? The unique mass here, 55 kilograms, and then the one that we're figuring out, which is weirdly in grams. All right. We're going to answer that later. All right. Let's put the number 5 in here. All right. And the length is 2. This one is unknown, so we'll just keep the letter M because we don't know what it is. All right. And then this is in centimeters. You have to change this to what it would be equivalent to in meters. For the sake of consistency. If there's meters here, then there should be meters there. So 400 centimeters is 4 meters. All right, so you're going to put a 4 here. That means that what you end up with is basically this. 5 times 2 is 10 on this side of equals, and 4 with it in front of an M on this side of equals. If you wanted to solve for this particular mass, you would have to cart this 4 coefficient over to here via the game of techniques of algebra. What's the opposite of multiplying by 4? Divided by 4 here. Divide by 4 here. This is just a number divided by a number. So that would be what? 2.5 would be the mass. All right. Now, I left out the units. All right. The unit here is kilogram. All right. And this one doesn't even, we don't know yet. Right. But again, for the sake of consistency, for the same reason that you could cancel the accelerations, all right, therefore they are irrelevant. The unit, and this was meters and this was converted to meters. We have to have some kind of consistency to start with. This is kilograms, right? 2.5 kilograms. If they're weirdly asking you, as they did in the case of my lab, what would that be in grams, you'd have to convert this to grams as an afterthought. What does that mean? It means, since you're converting from kilograms to grams, this is mass, not meters, all right, you're going to multiply by 1,000. So what is it actually? The mass over here is equal to 2,500. Pardon me. No, wrong thing, I'm sorry. 2,500 grams. Right. This is the way it's phrased. Okay? Okay. Yeah. All right. Moving on. Okay. Here you have imperial units being converted to metric units. All right. So we're going to pull the same technique basically, which is that whatever is given to you, you're going to multiply by an appropriate conversion factor, and that will give you what you want. Okay. Just realize that the conversion factors are written sideways rather than the style of a ratio. All right, no sin in that. All right. 2 gallons into liters. You're given 2 gallons, so you're going to put 2 gal times something is going to spit out liters. Right? Go to the conversion factor that relates to 2. Right? If you want to cancel gallons, then gallons has to be in the denominator. If you want to end up with liters, then that would be above the line. All right? If the relationship is 1 to 3.8, 1, 3.8, it would be 2 times 3.8 eventually, and you end up with what? 7.6? Or 6 point, no, 7.6, yes, liters. Okay, next one. 5 kilograms is what you're given. 5 kilograms times, you want to figure out how many pounds it is. If you want kilograms to cancel, kg has to go down here, lb has to go up here. The relationship is 1 pound, so the 1 would be here, is 0.45 kilograms, 0.45. The way that it works out is that you're going to end up dividing 5 by 0.45 because it's on the bottom. And the result is 11 approximately. It's 11.1 repeating, so it's 11 pounds. Okay. Miles MI to kilometers, I'm sorry. In this case, given 80 miles, you're going to convert using a conversion factor, and you want it to spit out kilometers. So, if you want miles to cancel, you put it below the line, you put kilometers above the line, you have a direct relationship here. 1 mile is 1.6 kilometers, so it's really 80 times 1.6, which is 128. Right. Okay, the geometry questions. I need to shrink this a wee bit. And I wonder what time it is. Oh boy, 3. I'm gonna try to finish this up before it hits 4. I'm not halfway done. Using the diagram above, what is the intersection, that is the overlap only, of ray FB and ray EB? Now remember that if they purposely put the letter F in front, that's the starting point. So FB would run from here through B in this direction. Right, yes, it would bypass the letter B because it's a ray, right, not a segment. Right. If we're talking about ray EB, right, that would start here and run through B in the opposite direction to infinity that way, because again, it's a ray. The starting points are really what is very important. All right, F starts this one, E starts that one, so that's why I'm kind of exaggerating. If we're talking about an intersection, which is what the horseshoe shape means, we're concerned with what the overlap is. Well, what is just the overlap? It's from here to there, all right? So how would you abbreviate that? The end point here is E, and the other point here is F, and in theory, you could write it backwards in this case, because we're talking about a line segment, but it would be logical like so, it's alphabetical. And the symbol would be this. If E, for whatever reason, and F, for whatever reason, were not included, then you would put a hole here and a hole here, but if it's both of those things, then it would have to be because they overlap to that extent. It's segment EF will that. Okay. For these down here, determine the measure of the specified angles. Okay. What you have are corresponding angles, alternate interior and alternate exterior. What one could say about M2 and the value here, measure of angle 5, is that these are corresponding angles, and therefore they are equal. So 5 is also equal to 26, right? At the same time, the relationship of these adjacent angles, 5 and 8 is the one we're looking for, these have a supplementary relationship, which means that they add up to 180 degrees. So if you know one of them is 26, 26 plus angle 8 is equal to 180. Subtract 26 from this, and you will get the balance that would be the obtuse angle here. So that's 10, that's 7, that's 4, and that's 5. 154 degrees. Right? This is 154 degrees. Right. There's more than one way to do this, all right, but those are to me that was the fastest way. If I need to know 8, then I need to know what's adjacent to 8, which happens to be 5. What is 5 in relation to the given thing? They're corresponding angles. Corresponding angles mean that they're on the same side of this transversal, but one inside and one outside the parallels. Okay, let me just roll that. The sum of the measures of the interior angles of an n-sided polygon. I don't know why I lost my ability to speak there for a moment. N-sided polygon. Remember, a polygon is a many-sided shape. Flat. That is two-dimensional shape. Right. So if it's n sides, it's whatever it is. A triangle has how many sides? N equals what? 3. You could calculate the sum of the interior angles of any polygon using this formula, using its number of sides. So if it has 3 sides, it's 3 minus 2, which is 1. 1 times 180 is 180 degrees, which is the definition of the interior angles of the triangle. All right. You're going to kind of use that again, but a little bit differently here. All right. Given what is true about regular polygons, to say that means that they are equilateral, meaning the side dimensions are all the same. They're not morphed in any way. They're not distorted. And equiangular. Right, which means that all of the interior angles are the same. Equal. All right. If something was not a regular polygon, in theory, one side could be a little bit longer than another. This isn't drawn very well, but I tried to specify that it's equilateral, all right, meaning all those are the same dimension, whatever it is. And if it's equiangular, this is regular, all right, then the angle here, whatever it is equal to the angle here, and here, and here, and here, and here. All right. This is what type of shape? All right. What must the exterior angle be here? We need to figure out the interior angle first. All right. If this is 1, 2, 3, 4, 5, 6, all right, then the total interior angles can be calculated from this formula. All right. 6 minus 2, which is 4 times 180, 0, 3, is 720 degrees. Now, that happens to be 1, 2, 3, 4, 5, 6 of these. If we wanted to get any one of them, but especially that one, we would now divide by 6, which means that they're all 100 what? 120 degrees each. All right. If this is 120 degrees here, and the relationship between these two is supplementary again, then we know that they would add it to 180 total. So 180 is equal to 120 plus whatever the question mark is. Right? So therefore what we do, we would subtract from 180, and you get that this question is 60 degrees on the outside. Okay. The next one is a picture about congruent figures and similar in proportion. Whereas congruent figures are completely equivalent in terms of their angles and their side lengths, similar figures, gobbledygook, distracting. similar figures are proportionate. That means they're not the same size, but they're each of the dimensions, they have corresponding sides, which although are not equal are either larger or smaller by some consistent factor. They're proportionate, right? As if you shrunk the original shape or you simply enlarged the other shape, but you didn't distort it somehow. All right. Taking this into consideration, use something called a shadow reckoning to write a proportion equation, and then indirectly determine the height of the tree in the diagram. I modified this from my original, I stole the original figures from my lab, and it just, even though it was correct the way that it worked, it just seemed a little bizarre to me that the height of the tree was so large. All right, if you write a proportion, all right, equation, then first of all it's an equation, so you're gonna have that sign, but you're using two ratios, all right, two fractions essentially. So there's a top and a bottom on each side. Be consistent, right? We're talking about height here of a tree, and we're talking about a shadow length, right? What I would do for the sake of consistency, and there's more than one way to do this, granted, is make the tops on each side the heights, and the shadow lengths on each side the bottoms. Make this one in respect of the tree, make this one in respect of the human. Okay, now, height of the tree, unknown, so we're just going to keep the letter H here. Height of the person, 5 feet. Okay. Shadow length of the tree, apparently 20 feet. All right. Shadow length of the person, 8 feet. Okay. Now you have a proportion equation. You have 3 out of 4 parts filled in, so you could infer what the missing thing is. How so? Cross multiply. Cross multiply this way, you cross multiply this way. This is getting to be a dud. I gotta press harder. That's how it works. Alright, so the abbreviation for 8 times h is just 8h, but I'm gonna be a good guy and I'm gonna put the 8 in front. Right. The multiplication of 20 times 5 would technically be over here. Right? And yes, you could do 20 times 5 and just simply write 8. There's no sin in that. What I have learned to do is to kind of hold off doing the actual multiplication because maybe I don't need a calculator. You know, I could make it easy on myself if I'm very strategic. So I'm just going to write fake multiplication here, that what would happen. If I'm going to solve for this as I would algebraically, that means that I must divide each side by 8 to isolate the h. We'll cross out the 8's here, leaves me with the height that I'm looking for. Now I have this. Because this is factored, what I can do without involving a calculator is try to simplify up front. Again, it's no sin if you have 100 over 8 and you just simply divide that and get the answer. But if you're trying to be strategic, these have similar factors. They're both even. In fact, they're both divisible by 4. So maybe I can get away with doing something here. 8 divided by 4 would be 2 left over, and 20 divided by 4 would be 5 left over, which means that this is 5 times 5, which is 25. And then this is asking me what's half of that, and it would be 12.5. 100 divided by 8 is 12.5. That is the height of the tree. Feet. Right? Using these dimensions that I quoted to you. All right. Now, this is to calculate an area and a perimeter, and then an area and a circumference, which is the same thing as a perimeter, but for circles. So let me make some space here. All right. Area here, perimeter here, area here, circumference here. All right, sorry for the faintness of that. In order to answer the area, what we actually have to use in the case of this triangle is the Pythagorean theorem, which solves for sides, right, first. The area formula of a triangle is this. Area of a triangle is the base times the height divided by 2. We don't know what the base is. Right. We do know that the height is 20, so we'll stick a 20 in here temporarily. Right. To figure out base, I would have to rearrange this formula, right, to solve for b. Now, I know the hypotenuse c, and I know the length, the height of it is all standing in a. All right, so the way that it would work out, a squared plus b squared equals c squared. If it's really, if you want to change the labels, h squared plus b squared equals c squared. I'm just going to rearrange this so that the a or the h, whichever you like, is sitting over here. So b squared would be equal to c squared minus h squared. And then, before I even stick numbers in this, I'm going to simplify this down to just b. Notice it's b squared. The opposite of squaring is to square root. So I do the whole thing. The bottom line is that this will cancel this. The formula that we're going to end up using is essentially this derivative of, not in a literal sense, in a calculus sense, but in a verbal sense, of c squared minus a squared. All right, or h if you like to call it that instead. Anyhow, this is 25 in here, and this is 20. You do the guts of the radical first. Do the squaring, then the subtracting, then you take a square root. 25 squared is 625. 20 squared is 400. The difference is 225. The square root of 225 is 15, which means that this is really 15 times 20. And if you want, you could pull a similar trick to before, which is that since it's factored technically, since you're multiplying, you can get away with simplifying. All right? That is, either do brute force 15 times 20 and gets 300 and then cut that in half, or simplify this and you get the area is equal to 150. If it's inches, then it's inches squared. Right. As for the perimeter, it's just the sum of all sides. And since you now have all of them, that would be 25 plus 20 plus 15. 25 and 20 is 45, and 45 and 15 is 60 inches. Okay. Now for the area of a circle, the area formula, I'll put this in a different color, is the area is equal to pi times the radius squared. You have to square it first. Kind of hold off on using pi until dead last, because you're going to get a number that infinitely stretches. Anyhow, the radius is 10. If you square it, you should follow the order of operations. If you square 10, then you have 100 with pi attached to it. I know it wasn't in the front, but legally speaking, you could put it there. If you know that pi is 3.14159, whatever it is, multiplying by 100 just has the effect of doing what? It moves the decimal place twice to the right. So what do you end up with? You get an area that is, if you're rounding it to the nearest hundredth, it's about 314.16. And since it's centimeters and we're talking about an area, it's centimeters squared. If you're calculating the circumference, which is the idea of perimeter but just applied to circles, all right, what you would need is this formula instead. Circumference is equal to, usually it's written as either 2 pi r or pi d, as in diameter. Since they gave you a radius, I'm going to go with this incarnation of the formula. All right, and we're just going to put a 10 here for the radius, right? And then we're going to do the multiplication of 2 times that first, because legally speaking you can, which makes it 20, and then it's times pi. All right, now again, as dead last, you are going to either use the pi button or whatever you have, 3.14159. That makes this, essentially, something that's 6.28, whatever it is. All right, what it should be, if you're going to round it again to satiate the requirements of the problem, it would be 62. 0.83 centimeters. And notice that it is in degree 1 because it's a a linear measurement, one-dimensional, I should say. Just unraveled, you know. 62.83. All right. Down at the bottom here it says find the number of faces of polyhedron. Remember, a polyhedron is basically a solid, you know, a three-dimensional figure. Many-sided three-dimensional figure with 13 corners, that's 13 vertices, and 15 edges. All right. How many faces would it have? Euler's polyhedron formula can be used. All right. The vertices is 13 minus number of edges is 15, and then we have faces. And it always equals 2. So 13 minus 15 plus f for faces equals 2. If you combine these, you get negative 2. Now, if you solve this algebraic equation to isolate f, you would just drag negative 2 over here. You do so by adding, it's a cancellation effect, and you add here. The number of faces would be 4. Okay. And now you have these two, which are a little tricky, because you need to figure out a slant height in one case. The volume of a square-based pyramid is this, which is small. The area of the base is represented by capital B times the height, times 1/3, so essentially dividing by 3. Right? They use this formula, capital B, the area of the base, because you could have different type of bases, right, for pyramids. So let's just say you had a square one. All right? You would need to figure out the area of the base, which is not too tricky, right? If it's truly a square, then the dimensions are 8 by 8, right? Which makes this what? 64. And the height of it is given as being 12. And again, you could multiply 64 times 12, or take advantage of the fact that you have a 3 here and simplify first. 3 divided by 3 is 1, 12 divided by 3 is 4. So it's just 64 times 4. Which is 256. If it's centimeters, as it should be consistently, and it's a volume, it's centimeters cubed. That's the whole kit and caboodle. Right? Notice at the bottom, instead what you're asked, it's the same pyramid, but it has to calculate the surface area. All right? It is a little bit trickier because the surface area is one triangle that runs this way, another triangle that is the front of this way, this other side triangle, and then the one in the back. So there's 4 triangles basically, and the bottom. Right? The surface area would be the 4 faces, right, plus the bottom. Right? In order to calculate the area of the face, right, what you need is to get something called the slant height. I'm scribbling a little too much, so let me just erase, and I'll use a different color. This line that is connecting from the top vertex here down the front side, slanted as such, is going to be a hypotenuse, technically, of this interior triangle. But this hypotenuse is the slant height. And we need that because remember, the area of a triangle is the height times the base, divided by 2. And we already have, we can figure out what the base is, it's 8. Alright, now as for the dimensions of this blue interior triangle, which happens to be one of the dimensions, the hypotenuse is the slant height. Alright, we could figure out, if this is stretching from dead center down to the center here, alright, and this is a square that it's 8 across, the dimension here is 4, right? The height from here to here is still 12, right? So c squared is going to be equal to a squared plus b squared according to the Pythagorean theorem, right? And it's going to be base, I guess you could call it 4 here, 4 squared, and 12, right? Which is 144 plus 16, 10 carry the 1, it's 160.
c squared is equal to 160. So what is just c then? Well, you'd have to employ opposite operations at this point. This cancels this. The slant height is technically the square root of 160, which is a terrible number because it's irrational, right? But you could simplify it if you want to. Now, here's how you would do that if you don't remember. Remember, if you have a square root and you want to just preserve the exact answer rather than using a calculator, it may not be practical in this case. Reduce it to a perfect square and then whatever the balance is, all right? Square root of 16 would be 4, so this would be the same as saying 4 times the square root of 10, if it's more practical in that fashion. All right. Now, we're going to get the area of this face, and then multiply it by 4 because there's 4 of these, right? 4 faces. So let me free up some space here. All right. If each of the faces is a triangle, and the area of a triangle is the lowercase b over 2, and they'll all be identical in theory, so this is going to be times 4 ultimately. I'll start to fill in some numbers here. The slant height, which is that much of the triangle, is the square root of 160. All right, I'll see if I can get away with using that. All right, and the base is 8. Right? So this is either 160, or you could say 4 times the square root of 10, and you could say that this is 8. So this is 8. All right. There's a lot of tricks you can pull here, all right? But let me do the rest of it here, all right? The other portion of this is you're going to add the bottom, which we already know. The bottom is 64, all right? Because this is a square. So that's 64. All right? This is 8 times 8. I would, because we're incorporating an irrational number, the square root of 160, try to rig it so that if you type any of this into your calculator, that you're reserving that for as long as you possibly can, because you don't want it to be rounded in the middle if you can avoid it. All right? So I'm sorry, I'm combing my hair because I look ugly. I still do. Alright, that's slightly better, right? Not really. Anyhow, you have a bunch of factors here, as you see the dots. This is on the outside, granted, ultimately, and there's a dot here because it's the base times the height. You can, for that reason, take advantage of the fact that there's a 2 down here and simplify it, which means that you can simplify the 2 and the 4, you can simplify the 8 and the 4 if you like. All right. I'm going to simplify the 8 and the 2 here. I should say, yeah. Okay, 2 divided by 2 is 1, 8 divided by 2 is 4. All right, that means that it's 4 times the square root of 160, which coincidentally on the outside would be 16 times 160, plus 64. This is what I would type into my calculator. Because this happens to be an irrational number, 160, you could see from attempting to simplify it, 4 square root of 10, you can't make it go away. Right? So you have a number that would end up having to be rounded. Round dead last. Right? So enter this into your calculator as you see it, and what you should end up with is what? 266, about, nearest hundredth, 266.39 centimeters squared, it should be, because it's an area. Okay. I'm a little suspicious, so let me just do that. All right. 16 times the square root of, 160 160, 164, yes, 266.385, surrounded to the hundredths place is 39, very good. Okay. Alright, now we just went through this next stuff, which is from chapter 12, so I'll go a little bit quicker here. Alright, you have to decide for this slew of problems, what is the sampling method that's being used. Okay. Alright, so it's kind of multiple choice in a way. Oh, blue, go away. Alright. Every 12th person, nth, in a line buying tickets is asked their age. Is it random, systematic, cluster, or stratified? Whenever you see something TH, well, I should say ever, you should check what else is being described. It's a good bet, it's systematic. It's like decimation, every 10th person, you know. Number of people are first classified according to age, and then, all right, random samples of people from each age group are taken. All right. This is called stratified, because you group first, all right, then you take random samples from each group. A sample consists of a random selection of entire groups, all right, or units. A lot of times this is geographical in nature, right? If you take an entire group, you didn't organize the group to begin with. You just took the box of pens, or you took the 100 square blocks of people, or the entire building of people, right? That's called cluster sampling, right? When you're talking about entire groups, all right? Lottery balls in a bin are shaken and then randomly selected, all right? And then selected without looking, that is random. I kind of gave it away in that case, all right? So first one is systematic, stratified, cluster, random, in that order. Okay. Here is a survey that has been formed into a pie chart. When you have a problem like this, it says the total annual revenue, the annual cost of the university is $16,000. Use the information from the pie chart to calculate the dollar cost specifically of tuition. All right, so if tuition is blue, it's 39% of that, 33.9%. 33.9% of 16,000 can be translated into simply 0.339 times, because that's what it is, 16,000. Right? And what you should get is 5,424. Okay. All right, when you do this one, all right, this is from test number 3. You have a data array. It might be out of whack, in this case it certainly is. So if you're trying to organize this into a stem and leaf diagram, what you should do is, in this case, you're constructing it by tens places, so 80s, 90s, 100s, 110s, 120s, 130s technically, and that's what the stems are here. And then try to put it in numerical order. I don't want to do it because it will take a little bit of time, but when you're doing this, when you go for the 80s, for example, cross them out as you use them, so then you have less and less as you're going through it. What you should get is this: a 6 here, a 0 here, a 0 and a 6 for the hundreds, and then most of the data, which is what the question is asking for, resides in, this is where most data is in the 110s. Right. Down here you have 2, 3, 3, 3. This happens to be the mode. Right, and this is 131. Taking this array, it would end up looking like this, which is basically a histogram sideways. The benefit of drawing a stem and leaf plot, a diagram, is that it will show you, as long as you put it in graph paper like this, so that there's a consistency in the increment that you're using, it will preserve you could see the individual data values, what their actual value is, but also it will illustrate where's the highest frequency, all right, in this class, the 110s. Okay. All right, this one here is a similar situation. This is the process of basically building a true histogram. That is the one that is oriented more or less vertically. All right, but without torturing you and myself, what you would do in this instance is establish the breadth of the group categories, right, based upon what the minimum and the maximum are. They ask you specifically, in this case, to have 6 classes. So if it goes from 1 to 18, all right, what you could say is that they're 3 wide each, all right, because you're dividing by 6. If this is approximately 18 long, divided by 6, they're 3 wide each. So you have things from 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15, and 16 to 18. And these are your 6 classes, right? And then I put in this extra column here, because a lot of times I don't give you that, all right, to keep a tally while you're going through this array, right? And what you should get in that case is basically this, that there's 10 things in this in this category, 14 in this, 10 in this, 6 in this, 5 in this, and then 5 in this. Okay. Notice that the maximum frequency is 14. Okay. Now, if you're going to go and use some formulas, right, relating to the same problem, here's how you would reason this through. Right? We have the classes already established. The lower limit of the second class is, if it's 1 to 3 is the first one, and the next one is 4 to 6. The lower limit of the second one is 4. All right. The lower limit of the first one is 1. That would establish that it's 3 wide. All right. We already know that from dividing by 6 anyway, but that would be consistently true. Right. Must be consistent throughout. All right. So if you did the next one, 7 to 9, say hypothetically, and you put that number here, 7 minus 4, instead you get 3. The width of the columns has to be consistently true throughout the histogram. All right, this thing is the class mark, is more or less trying to identify what the middle is of each of those. All right, if you borrow information from the first class lower limit is just 1, and the upper limit of the first one is still 3, and that would be 4 divided by 2. The middle would be 2. Right? So this is the midpoint of first. All right. And this is how wide it consistently true. When you're answering this question, using the class mark and the class width, list the 6 midpoints for each class. That basically is, if 2 is the first one, we're going to circle that to keep it. The next bar would be 2 plus 3, which would be 5, circle that. The next one would be 5 plus 3, that's the midpoint, and that would be equal to 8. And the next one would be 8 plus 3, which would be equal to 11, naturally. And then 11 plus 3 would be equal to 14, circle that. And then the next one, the last one, would be plus 3 would be equal to 17. All right. These numbers, 2, 5, 8, 11, 14, and 7, are the midpoints. Now, the way that I wrote this problem is that can kind of help you draw the picture. I'll zoom in a little bit on this now. All right. Now, using each of these, and let me just back off a little bit. Using these midpoints, as something of an x-coordinate, but not really, all right? And in tandem with the frequency, this is something of a y-coordinate. You can kind of use it to make dots on this piece of it. We're drawing a histogram, so it's a bar chart, but that might help a little bit. What you should do really first is increment this down here, all right? All right, these are the classes down here. Every histogram has a horizontal axis that is classes, all right? And it would be, it doesn't have to start at 0, but in this case it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. They're in between the increments, basically, the way that I've done it. And on this side, you have the frequencies, which run vertically always. All right, this tops out at 14. So what I'm going to do in this case is I'm going to label them right on the line as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We don't need to go further than that. All right, now, again, if you treat these as x's, right, then we can treat the frequencies as something like y's, right? For the first class, the y value was 10. For the second class, the y value was 14. And then for the third, it was 10 again, and then it was 6, and then it was 5, and then it was 5. So that more or less, you're going to put a dot at the location of 210. So right smack in the middle of this 10 block, this 2 block, go up to 10 and put a dot there, just temporarily. And then go over to 5, right smack in the middle, you're going to go up to 14. So that would be there. Okay. And then 10 is 8. 8. Right. And then 6 is 11 here. At 11, you're going to do 6. So that's there. Alright. And then at 14, you're going to do 5. So 1 shy of it. And at 17, it's just coincidentally the same thing. Okay, now we know class width is 3 blocks wide. Okay, so if that's the middle, that's 3 blocks there, that's 3 blocks there, that's 3 blocks there, and 3 blocks this way, and this way, and this way. And now, you're just going to draw lines to simulate bars here, like so. Okay, and that's a histogram. Now if you want to fancy it up a little bit, what you could do is try to shade it or color it. I end up doing this if I just have like a pencil or something. Put sort of a crosshash or half of a crosshash at alternating pattern here to make it obvious that these are distinct bars. If you were going to do a frequency polygon, you'd have 1 extra class this way and 1 extra class this way and a dot down at the bottom of each, and then you would connect the midpoints to superimpose it, but you don't have to do that. Okay. A lot of the stuff that follows, you end up using the calculator. Let me see if I can get this in one shot here. I'm at 4 hours almost. Right. Using the data array here, you could do this by hand. A lot of it you could actually use a calculator, but a good habit is to put them in order first. So I know it's out of whack, but this would be 1, 1, 6, 8, 12, 13, 14, 22, 25, and 32. 34 rather. Right. Rank these first. When they're given to you, don't assume that they're in order. Do check it. Alright. To answer things like median, you really have no choice. Alright. and mid-range as well. Alright. So the mean in this case, the way that it works out, if you add all of them, and then divide by how many there are. X bar is equal to 13.6. Because there's an even amount of these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there's 2 that land in the middle. The 2 that land in the middle would be averaged. So 12 plus 13 divided by 2 is 25, cut in half, which is 12.5. Okay. The mode would be the number that happens to repeat the most often, which in this case exists, it's a 1. And then the mid-range is the high number plus the low number divided by 2. It's kind of a cheesy average. Mid-range, which in this case would be 34 plus 1. Divided by 2 is 35, cut in half, which is 17.5. Okay. To calculate 55, if a student's test scores are 80, 86, 73, 91, what would they need on a hypothetical fifth test? Minimally, right? Minimally implies greater than or equal to get at least an average of 80. So if you want at least something that is greater than, something that is minimally is saying at least is saying it's equal to that or it's better. So in this orientation would be greater than or equal to 80. What you would have is a sum of 80 plus 86 plus 73 plus 91 plus this fifth test. So I'm just going to put n for fifth. Yeah. Divided by 1, 2, 3, 4, 5. All right. And you manipulate it. All right. Move the 5 from here to here. That makes this 80 plus 86 plus 73 plus 91, which is, I forget offhand, something huge. 80 plus 86 plus 73 plus 91, 330 plus n is greater than or equal to 400. You subtract 330 from both sides, and that hypothetical fifth test must be a 70, or better than a 70, to get at least an average of 80. For this data array, there's a formula which your textbook does not include, but my lab thankfully did, and I'll put it here. If you want to find the position, I'll do this first. Using the data array, the number of months for employees that stay at their job, what would be the percentile rank? It's already in order, so you don't have to do anything. What would be the percentile rank of the person at 36 months, which is right there? All right. What is the number of data that are below that? All right. If this is an array of 3 by 9, there's 27, right? Which makes this 27, 26, 25. There are 24 below 36. And there are 27 in general. So if you have this fraction, 24 divided by 27, and then you multiply by 100, what you'd get is that this is approximately the 89th percentile rank. Okay? When you're using the same information to answer this question, using the data array, you can do it brute force to figure out what the quartile 2, the quartile 1, the quartile 3 are. Quartile 2 is the actual median of the data. So you could figure that out in brute force. But what might be helpful is to use this formula, right? The position of the median can be calculated in one of two ways. It's the same formula, but just described differently. The sum of the frequencies plus 1 divided by 2, right? Or, which might be intuitive, the number of data plus 1 divided by 2. So you might end up using that incarnation of it because nothing really repeats in this case. All right. There are how many data points? It's an array of 3 by 9, so it's 27. All right. So if this is 27 plus 1, that's 28. What's 28 cut in half? The 14th is Q2, right? The actual median is the 14th thing. So you're going to count, all right? From here to here is 9. That's 10, 11, 12, 13, 14. Quartile 2, the actual genuine median of the whole thing, is 17. If you're now going to calculate quartile 1, you need to incorporate everything that's before that, right? So you just modify this formula, right? It's n plus 1 divided by 2. We're going to figure out what the position is. You can count it. It's not something you could certainly do a brute force, but this is kind of cool. All right. How many data values are under 14? 13. So if this is really 13 plus 1 in the formula, that's 14 divided by 2. That's the 7th thing. So from here, 1, 2, 3, 4, 5, 6, 7, that's quartile 1 is 9. All right. You don't really have to do it again because we already have the median. So 7 above or below quartile 2 is what quartile 1 and quartile 3 are. All right. Quartile 1 is 7th below. All right. Quartile 3 would be above. So from middle here, 1, 2, 3, 4, 5, 6, 7, 24 is quartile 3. Okay. Now for the next thing, again, I would use my calculator. Using the following distribution, they're in order, 3, 4, 7, 12, 14. Calculate the range, the mean, and the standard deviation. For the latter two, use either the formulas or you could use that. All right, range, mean, and standard deviation. All right. In your calculator, the standard deviation would be the thing designated as x. All right, and mean is x bar. Range is just the high number minus the low number. So it will be 14 minus 3, which makes this 11. All right, the median, the mean would be 8. If you add all of these and divide it by 1, 2, 3, 4, 5. All right, the sum divided by 5 is equal to 8. And if you calculated the standard deviation, which is something like an average to and from this number, that is every data value averaged as its distance from this value on opposite sides, you get something like this. S is about equal to, this is a long figure, 4.85, something like that. Okay. Now, this is a fun fact which is good to know. When you have skewed data, the lump is stretched, right, because of some suspiciously large or suspiciously small figure. All right, if in a normal distribution, mean, median, mode are all the same number. All right, and they all appear in the dead center, which is cool. There's symmetry. All right. However, when the distribution curve is skewed, either towards the left, which means that the tail is on the left, all right, or skewed right, which means that the tail is on the right. All right, these values are distinct from each other. Label the lines of each diagram in the proper order from left to right using these three averages, mean, median, and mode, right? The median is always in the middle, which is why in a situation like this, it's probably the most reliable figure. So you can put them here and here. Okay. The mean is the thing that gets pulled away from the pack here. So this is the mean because of the tail being stretched right. And the mode would be the very tippy top of the lump, right? The most data, you know. Same thing here. The mode would be basically the top of this. Alright, and the mean would be stretched lower in this case. Alright, so on this side, skewed right, mode, median, mean, in that order. Mode is less than the median is less than the mean. In this case, the mean is less than the median is less than the mode. Okay. Moving on is 60. All right. The time of a phone call to Cablevision, probably to complain about the bill, is normally distributed with an average duration of X bar as 2.3. Label that here 2.3. And a standard deviation of 0.8. We're going to use that in this formula. All right. What percent of calls last between 1.3 and 2.8? In respect of 2.3 in the picture, 1.3 would be here. And in respect of the picture, 2.8 would be on that side. All right. And if we're asking about the calls between, we could calculate the area that is in between these. Now the way that you do that is the areas are always, whether you use a table or use calculus, right, are read from here to there, right, from left to right. So this would be a larger area, in theory, if you were to calculate the whole thing, right, from here to there, not just a portion of it. If you were calculating the small area, then you would still start from the far left, and you would go up to this line here, small area. So the area between will be equal to the area that is larger minus the area that is smaller. But before we can even get that far, what we have to do is we have to calculate z-scores. All right. So you calculate two z-scores using the standard deviation and those values that are relevant. Basically, it looks like this. I'm going to label it like so. The z-score that is based upon the figure of 1.3 would be the value that is 1.3 minus the mean, which is 2.3, divided by the standard deviation of 8. What this is accomplishing is it's calculating this thing's unique distance to the mean out of what the standard deviation ought to be, right? And it will give you a ratio, right? If it was, you know, exactly 0.8 up here, then it would be 1 to 1, you know? It would be 1 overall, right? But things are not always like that. So then in this case, you have the z-score of, what is it, 2.8? So this would be 2.8 minus the same average of 2.3 divided by the same standard deviation. So it'll give you another thing that is, you know, whatever proportion, all right? In this case, all right, what you're going to get is a positive number, right? And in this case, you're going to get a negative number up here. So this is going to be negative 1.25 for the z-score, all right? Which we're now going to look at the table, all right, of z-scores. All right, and this will correspond to an area. This is going to be a little bit trickier because of the numbers involved, but you don't have to be that precise. I think even I stole this from my lab, and I don't think they had the precision that I used. Right? There's a patent they sold in the back, right? Okay. This is a z-score of 0.625. Right? The precision of the table only goes to the hundredths place, so you could finagle something. Anyhow, this is a positive, and that's a negative. Right? If you go and you look in the table that is available here, you would look at negative 1.5. I'm going to show you here. Negative 1.2. This first digit here, the 4 digits here, is 0.20. So that makes this 0.21, 22, 23, 24, 25, which means the corresponding area for a z-score of negative 1.25 is this, 0.1056. Right? That's a fraction, basically, of one whole. Of 1. Okay? The whole area would be 1. Right? Now, when you do this one, positive 625, you have to look at a different table here. This is 0.6. It's going to actually be in between. Here's 0.6. Maybe I'll zoom in on this a little bit. There you go. Here's 0.6. We're looking at positive 0.625. Remember, the precision of the table is just for these columns are the hundredths place. So we would have a figure that would, be, in theory, be in between two. All right. I forget exactly what my lab had suggested. I think they wanted you to round up, but we can figure it out anyway. All right. So here's 0.6. That's 0.60. Let's see. 60, 61, 62, and this would be 63. All right. That's like comparing um, 0.620 and 0.630. Right. The precision again. They stop here at the headings of the columns. What's my place? 0, 1, 2, 3. Right. But if you gave it an extra digit, one could assume 0, and that would be 0. So it's like comparing 20 to 30. All right. Anyhow, 25 is what we have. So our figure would be exactly in between these, right? If the areas that are being quoted to us in these columns, I gotta figure it out again, 0, 1, 2, 3, is 0.7324, and this one is 0.7357. Just figure out what the middle is of this, right? By taking an average of it like you would the median. Add these two, divide by 2. What would you get? You should get this. 0.73405. That's overkill, right? But that's exactly what it would be for this figure, 0.625. Right? I think again, my lab probably said, just round up. Yeah. But hey, we just went through the discussion of calculating median anyway, so that's what it would be. Yeah, I'm sorry, not to be temperamental. Going back here, there we go. Alright, back to this problem here. So, what is the area? Let me zoom out of this. Alright. It would be this figure, the larger area, would be 0.73405 minus the small area, 0.1056, right? And then what would you get? You would get 0.62845, which if you converted it to a percentage, they ask what percent of callers last between 1, 3, and 2, 8. Multiply this by 100. The effect is to scoot the decimal place over. You round it to a whole number. Wait, 62. Yeah, it's too dopey. It would be about equal to 63%. If you rounded it to a whole percentage. It wasn't specified, right? Alright. Last page. Alright, some of this is pretty straightforward. Alright. Judging by the scatter plot below, would you say that the data is a positive correlation, which means that as x increases, y also increases? Or is it a negative correlation, which is as x increases, y decreases? Or no correlation, which would be a jumbled mess? Right. If it is going, and this is x, and this is y, from the top left down to the bottom right, essentially like this. That's the pickle pattern there. And it's a negative correlation. Right? There's a relationship, it just happens to be in this situation. As x increases, y decreases. The pickle pattern. Yeah. All right. 6-2. All right, last one. You would definitely use a calculator for this. Okay. It is speculated that the daily high temperature for 7 days, that's day 1, 2, 3, 4, 5, 6, 7, in January, correlates to the number of cups of hot cocoa sold. Given the data array below, calculate the correlation coefficient. It's a linear correlation coefficient. And then compare this to the level of significance alpha, that's this table here, at 1%. So we'll be looking at this column specifically. For 7 data values, pairs of data. 7 is the n. To decide if there's a correlation or not. All right. If a correlation exists, find the line of best fit, which would be the equivalent of y equals mx plus b. And you could use this formula, but it would be better to just simply use a calculator again. All right. This will take, at least a half an hour. Anyhow, what you should get from inserting these values into your calculator, and it would be a calculator of this type, all right, is that your R value is equal to negative 0.936. Then, because you have 7 data values and you're comparing the critical value of alpha at 7, right, for 1% of significance here. All right. If the R value is greater than the alpha value, then there's a relationship. If R, the absolute value, is less than alpha, then we would say no relationship. It's a way of certifying that in terms of a probability. All right. At least at 1%. So, if you insert this value of negative 0.936, right, the outcome is that it would be positive 0.936, and that would in fact be greater than what is available here, 0.876. So there is a relation, right? And since there's a relation, then we will take the time to figure out a line described by y equals mx plus b that would predict this for something beyond 7 data values to extrapolate, all right? And then you could also get that from your calculator. Your calculator calls it A and B, right? Same screen. The A value in this case, all right, would end up being negative, as it seems to be projecting downward here. You would have this, negative 0.80x, and you would start at 76.10. That's your equation. Okay, and that is it. All right, this is a 4-hour and 18-minute video. Anyway, if you stuck with me, thank you. I appreciate that. And it's just if you took the time to do this, so that you have some satisfaction in knowing that you got things right. Okay, all right. Take care, folks, and thank you for a nice semester. Be careful out there.